going to share these things with them? Like all the
Slides we are sharing, whatever lectures are done, we are sharing today. Since tomorrow there is one exam for them.
Right,
It will
yeah.
be useful for them to.
But we can give additional slides and material later
That
on
we will do
also.
it slowly after the answer. We can do any additional.
Good morning, everyone. Welcome back to day 4 of GIAN course on adsorption techniques for carbon dioxide capture, modeling and simulation insights. So today our first lecture by Dr. Debanshu. This lecture will be on advanced isotherm and kinetic model development. This is followed by tutorial. So please continue.
Okay, thank you. Okay, good morning, everybody. So my voice is a little bit better than yesterday, so I hope it stays that way for the whole day. So praying for that. First, you saw that there is a difference in the in terms of the topic, that what was in your agenda, because we kind of covered that yesterday. Because these are some of the topics we thought would be very important for you to go forward, to understand that a lot of new materials that are being developed not necessarily follow the isotherm model that you get from the book or the literature. So this could be challenging depending on what type of novel adsorbent that you are actually developing. So I thought I'll discuss about some of those type of things. But before I go forward, I just wanted to check with you that anybody has any question regarding the cycle setup that we talked yesterday, like pressure swing, temperature swing, vacuum swing, or hybrid development. Anybody has any questions that we can just first discuss that, because that was the topic for today first. Okay, so but we'll be here through the whole day. If something comes up, just let us know here. So what I would like to mention here is that why I have this example problem here is that this shows you one of the cases where your isotherm model can be very, very challenging. So you could come up with the standard, all variants of Langmuir type of an isotherm, the BET type of isotherm, Freundlich type of isotherm, all combinations of Langmuir and BET type of isotherm. None of them will actually work. Anything in the literature or in the book may not actually work, okay? Because this could be very complicated. So the first thing what you really need to look into it, like for example, this particular one, generally when you look into it, what happens is that the working capacity is defined between your absorption temperature and your desorption temperature. So say here I'm adsorbing at this condition, and then when I'm desorbing here, because I'm raising this temperatures over here, this is really the working capacity. So you are the first point what you will remember here is that as we set up the Aspen AdSim model, one discussion that which we'll continue to do today and tomorrow also is that what is the initial loading of the bed? Is it free of any adsorbent? It is not. That is how we set up, but it is not. It is because the initial loading of the bed or initial condition of the bed is what you got from the previous run. So at the end of the desorption, whatever is the loading, that is the beginning of the adsorption in subsequent cycle. And it continues. So I start with a zero loading, it's a fresh bed, and then I run it, but I cannot come back to zero. I will end up somewhere here. And the next time I'm not starting from a zero loading, starting with some loading already in the bed, it goes up. Maybe it will not reach here, it might reach some other place. And then it keeps cycle and cycle and cycle. And after it cycles for many cycles, it will reach something what we call a cyclic steady state. I will keep talking about this word quite a bit, but this is an absolutely critical concept for you to do that. So sometimes when you start with a fresh bed and you see there is a breakthrough curve and it shows fantastic loading, that's not meaningful. Because you will not, next time you run the cycle, you will not land up at the zero loading. So remember this point, So something noted as cyclic steady state or often known as CSS. What it basically means is that the loading at the beginning of the adsorption at each location of the bed is equal to the loading at the end of desorption at each location of the bed. So if I am looking at a bed like this, so I am saying here, all the discrete point, this constraint must be satisfied. That gives you the true picture. And that is one of the biggest difficulty in simulating this type of systems, because the results you will get, you first must achieve a cyclic steady state. So AspenTech has got an option of saying run for the cyclic steady state. I'll show those options there, probably not today. Let's see how the time permits, maybe early tomorrow we'll show you this one. But this is actually one of the very difficult things. So for AspenTech, they keep running this cycles and cycles and cycles. We just never know when you will reach this cyclic steady state. Maybe you will reach after 5 cycles, maybe after 10 cycles, for 15 cycles. And that is what is one of the problem when you start doing an optimization, because when you are doing optimization, you cannot grab the results from the model at all, because the results are not meaningful till you reach the cyclic steady state. That's why a lot of work has been there in the literature where you put it as a constraint. You write this equation as an optimization constant and you force the optimizer to directly go to this condition there. So, but I just wanted to say this is a concept you definitely need to keep in your mind. However, if I could have a isotherm where it will actually switch like this. So most cases it goes like this. So these are the standard Langmuir type of an isotherm that you have actually looked into all the times. But the problem here is that your working capacity is not good and you never come to zero. But what happens is that if you adsorb here and it looks like a switch, then it actually gives you this opportunity. And what it does is you can move the switch, like where the switch takes place, at what temperature the switch takes place, here, 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 here. So if you have a material which will let move the switch, you can design the switch condition based on the temperature and pressure and other conditions that you wanted. So if you say my optimal temperature is this or my optimal pressure is this, so then I can move this. So that is the whole idea. And this type of material that, again, this is a thing that which I was actually describing yesterday. This was University of California, Berkeley, one of the functionalized MOF. It gives you a lot of opportunity to do that. So they can play with these three things over here to switch these things. So that's the whole idea. But now when it starts coming, this becomes, economically this looks good, but mathematically this becomes more challenging, that how to represent this type of an isotherm. So I will show you that basically what happens. This is a cartoon to give you that idea, but what happens here. So there are two of them that which we considered. So you see this looks like crazy, right? I cannot even say what chemical is this one, right? So, but this is they can play with all of this. So if you look into the original paper here, they can say, okay, what group they consider here, what they do here, what they do here, what they do here, and then the metal that they have Mg, they tried many things. They had the calcium, zinc, magnesium, many things, and say which works the best. So it has got a lot of flexibility, right? Again, I do not know how these are immobilized. I'm not an experimentalist, but this is how it is. So this type of thing actually works for a higher partial pressure, like a coal-based capture, right? So you see that how it actually drops, and then this is 100 degree. You see, it's actually a pretty steep drop that you will. It seems like the battery may be a bit low actually. Okay. So what happens here is that this drops here, but you see the nonlinearity of this type of an isotherm, and you can clearly see, like for example, if I'm going like this, I will not be able to capture this guy at 75 degree. It looks very different than any other things. And then you see 100 degree, it actually goes different way. So that's one challenge. Then they came up with another one, right? This is this chemical here. This is for the lowered CO2, and this has got 2 steps. So you can play with 2 steps, and depending on where you have, it actually can switch those steps, where these steps actually do appear. So this is again a complicated isotherm here. The interesting thing, you see that it does go here, but it does not go like a standard Langmuir type an isotherm. It does not directly go to this equilibrium loading. So it steps up, but then it keeps going actually. So there is a nonlinearity, and then another part is actually going there. So this becomes very challenging literature and modified it. So this is something known as weighted dual site Langmuir isotherm model. So some variations, but this is a weighting function, and these are really the weighting function. So you see that these isotherm, so there are 2 different isotherm model, dual site SIPS isotherm model and this one. It looks more complicated, and there are a lot of parameters also comes with this. So if you see these one are all the parameters here. So yesterday, as Professor Sridhar was showing you that how to obtain the isotherm parameters there, here the number of parameters that you will be estimating from a MATLAB based model or Aspen model or Python or whatever you are using, that becomes actually very involved. And because of the step-like approach, this exponential functions actually brings in that step-like approach. And then basically it shifts, it decreases one functionality. So you basically see this will become 1, and at another point it will become 0 actually. So this omega will lead to 1. So this time becomes 0, this term becomes 0, and this will be the prevailing term. So that is how the switching actually taking place. And there we propose these as, this is what we proposed as part of this work here, is a combination of chemical and physisorption. So remember that the reason that why it steps up is because of chemisorption, and then the thing that it looks very nonlinear in terms of how the isotherm actually looks like. These are the data which we did not use for parameter estimation, but use for testing. So we basically say, I do not know what it is, but you give me some data for 80 and 90, which is in between these two, and we will be testing it. So this is how it actually looks like. And you see that the SIPS isotherm was better, but this one at these points did not really capture it. So once again, it tells you that those problems that you solved yesterday for your MOF that you may be developing, for some of the advanced MOF that you may be considering, these can be, you may have to come up with your own model, and maybe nothing in the literature will actually work, because remember, most things in the literature that you will find has been developed for physisorption type of an isotherm, which are very well predictable. So isotherm type 1 and 2 and 3 and 4 that you have studied, right? I think Dr. Datta actually discussed all of those things. Those works for physisorption. Chemisorption is all kind of crazy things that are happening. Okay, because there's a chemical reaction, it's very complicated. So this type of systems, actually what happens is, why it switches like this, inside the cage of the metal organic framework, it actually forms a chain. And this is what they call the cooperative adsorption. When it starts, it almost looks like a polymerization reaction. The chain will propagate very fast, and that is how it gets that strength there actually. So this is very complicated reaction. So what they did was that they did some NMR spectra for all of this, right? So it's a nuclear magnetic resonance, right? And from there, they basically say what type of chemicals are forming within the cage, right? This is all micron size cage, but can I figure it out what is happening? So that's, they did that and provided those analyses there. There is that as you are increasing the partial pressure, these chain forms, and the moment the chain forms, they actually cooperate with each other, and they rapidly progress through the entire system, consumes entire chemical, and form something which is a polymeric chain. Actually, that's what is going on inside this one. So it becomes very complicated. So if you look into the results over here, you see that the SIPS isotherm, that the one that which I said that we modified it, was actually giving you better than the other one. So when we did this work, one simple thought came to our mind. Okay, maybe I will discuss this one and then I will discuss the other aspect. This is for the other one. So what we really do is that it has got two-step transition here. And the idea is that we could extend our previous model, right? And then with something like this actually. Like it has got now two switching. Because of two switches, there are two weights, W1 and W2. So they give you the two transition. So that was a natural fit. And then you see this model looks even more complicated. And then you can actually estimate these parameters in MATLAB or Aspen or Python, as I said there, right? This is how this new model actually looks like after doing the parameter estimation, right? So once again, that approach seems to be working, and you see this is also give you a log scale here. And here the idea was that we did not want to discard this low partial pressure, this part. We really wanted to capture some of those parts. The reason is so that if you go for direct air capture or you go for 99.99% capture, then you are entering this range. So we still wanted to have these. Thank you. Sorry? Uh-huh. Yeah. So this weighting is actually doing the weighting of the, so these functions, the W1 and all of this, if you look into this, these are changing between 0 to 1. So when you have got like, so what we wanted to have it is at one point in time, this is 0, this is 0. All of these are 0. So that means this is the main thing. Then W1 will rise to 1. This term will be 0. W2 is still 0. So this term will take over. So this becomes 1. And then at another point of time, this will become 1. So this is 1, 1. This will cancel. And then the third one takes over. So it's kind of a switching from 0 to 1, then 0, then 1, and then 0. That's what this, right, to capture those steps. So it looks intuitive, but those step positions, so why it looks like a function of, so you see, if it is just 1, it's a standard sigmoid function will work, right? Like for example, which we always use in machine learning now, like the standard sigmoid function. But now the step keeps changing actually. So where the switch takes place, changing. So that is a function of the pressure and temperature. That's why we had to consider all of these other things. So look into how it is. So this is a function of P, and then this is a sigma, and this sigma is a function of temperature. And then we had these exponents also. So it's basically, it's a complicated function of pressure and temperature, how the step, where it shows up, and how it keeps shifting with respect to pressure and temperature. You had a question? So this is, so if this type of fitting, like for example, when you look into Langmuir, SIPS, BET and all of that, as I said before, those have been developed for a physisorption, so which for the molecular phenomena that is happening, that can describe. So now with an approach here, what we are simply doing is that we are using some of the existing tools and extending that for application. Obviously, if you have a chemisorption taking place, these models are not, has not been developed for that. So it does not accurately capture what is happening. So mathematically, it gives a function that you can use in a model, but it does not give you any idea about what is going on. So you asked this question at the right moment, because I will now transition. So this was a thought that came to our mind, that the idea is, can we describe systematically what is going on inside the system, and can such a rigorous model can still be able to represent such data? So that's our next work. So I'll be presenting that part also. Yes.
Since the mechanism of adsorption is changing over the pressure range, should be this EA value, heat of adsorption, does it change with pressure region, and what is the typical values are like?
So we calculate is the isosteric heat of adsorption here for this one, and I will show you actually. So this is probably a question, I will keep it for now, and that actually is as part of this, because we are simply fitting the model. This is not actually considered that, but this actually, I keep this question now. I will show you that what happens to that heat of adsorption. It's an interesting question and thought actually, yeah. So this was the whole idea we had, and now we do the parameter estimations a bit. So then we started thinking that, okay, can this system be modeled? So this actually, what is happening here is that there are these, this is the typical cooperative adsorption mechanism that is taking place. So again, let's not spend more time into it, because we worked with a bunch of chemists and we proposed some idea, run it through the chemists at the University of California, Berkeley and Lawrence Berkeley lab, and they say, okay, this makes sense to us, and perhaps this may be going on. So we proposed a mechanism, and then we say, is our hypothesis look good, or that type of thing. So that is what is basically showing here, and then we are saying, okay, it may be forming different type of things. So we basically propose there are 3 types of product forming inside the cage of the metal organic framework. Maybe we are having some carbamate chains here, then we can have these carbamate chains, then we have the mixed carbamate, carbamic acid. These are all they found from their NMR spectra. It is not like our hypothetical thing. So it's basically they're finding it, and we basically say, yes, if you are forming it, this is the mechanism by which it can form. So that is what we proposed here. And then we also have the physisorbed CO2. So as I said, the NMR studies actually help you to identify the species, but that will not tell you anything about the mechanism that may be taking place. Okay. So then this is what we proposed here. So basically idea was that it will be forming an initial formation of adsorption product, then it will keep propagate, so keep propagating the reaction, and then the chain will be forming. So this, when it comes to BN, we are basically saying that inside the cage there could be material forming of different chain length. like n equal to 1, n equal to 2, it's like how the polymerization reactions take place. So inside this, it may have a lot of these chains getting formed here. Then you could have other species that could actually be forming. So these are the other reactions that might actually consider there. And then the idea was that how many such reactions might take place, what would be this chain length, this n and the m, and then we consider the estimate, the modeling products here. So when I say this basically meaning is that like we are trying to find out the carbamate chains here, and then we are also trying to find out the carbamate carbamic acid. Those both of them are getting forming. So question is how much of this is forming, how much is the other one is forming. So this was the thing that which we discussed there. Next come actually most difficult things. So remember, like there was some discussion, I think Professor Datta actually discussed quite a bit about the thermodynamics of it, so I do not want to spend much time onto this. Thermodynamics of solids is one of the most complicated one. Most thing we study in our undergraduate and graduate studies is thermodynamics for liquid and the vapor. So developing a thermodynamic model for solid gas systems becomes actually challenging. So this is perhaps one of the first shot at it. I'm not sure how much right it is, and some thermodynamics may say that there are opportunities for improvement. Obviously, I would accept that, and there are definitely opportunities. But this was something which we proposed. So fundamentally, the equilibrium for any systems, vapor, liquid, gas, solid, does not matter, or liquid, it's all given by the equality of the fugacities of those respective species. So if I'm considering CO2 is the only species here, then gas phase is standard. You can actually give it in terms of fugacity coefficient, so we get it from the equation of state, and then this is the part that becomes actually complicated. This is more follows similar to how you do for a liquid vapor system, because these solid systems has got nonlinearity. The problem, the thing that what you have to think about it is that when the molecules get adsorbed on the surfaces or reacts there, you are changing the surface potential of it. So what you are trying to find out from this type of systems is that adsorbent, with the adsorbent in it, what is the energetics of that whole system. So that is what this thermodynamic model is trying to capture. So we can start off with a standard activity coefficient model type, and then we expand it, right? So we consider this. So this is almost like looks like an activity coefficient part, and then we started off with a proposed multi-component Margulies equations. Margulies equations is used also for liquid, but this is something which we extended and proposed a multi-component Margulies equation. And then we had the reference state fugacities that which we are referring here, corresponding given by the Henry's constant. And then also, because the equilibrium reactions are taking place, we also needed to consider the equilibrium for those reactions there. So this was something originally proposed. Okay. Then you have to do the component and site balances. So the first thing is that you have got only finite number of sites there. So once those reacts, those chemicals are consumed, you have no other space for the reaction to take place. That is why it goes there and nothing happens, because every sites are consumed. So you must actually have a site balances over here. So this is, I'll not go over this time over here, but then this gives you chemisorption loading, physisorption loading, total CO2 loading. And then another thing is the standard heat of adsorption. This is an isosteric heat of adsorption, which we discussed before, like by Professor Datta here, and that is what we considered it. Now the question is, as I'm predicting all of these things, so there are two ways of doing these isosteric heat of adsorption. You run experiment, and looking into this, you take the derivative and calculate it. But here we are proposing a model. So in this case, we want to constrain it. So we are basically saying, no, we understand from that material they did calorimetric measurement, and they basically say it is not expected to be greater than 65 kilojoule per mole, or maybe at the most 70 kilojoule per mole. So I can come up with a model, but it must constrain that it should not be exceeding that, because there are multiple solutions. So this is comes with respect to the optimization. So when you do the optimization, what is the system boundary or the constraint that which we are considering? So the heat of adsorption is a constraint that you must satisfy to ensure that what mechanism you are coming up with, what parameter you are coming up with, is consistent with what is expected. So then, yeah, this is actually this leads to a mixed integer nonlinear programming problem, and these are our integer variables, like we are basically saying how many species are considering what blah blah blah, and I do not want to go really onto much of these, but these are all done in Python with some AML solvers and IPOpt as the optimization here. But yeah, but there are many other things that we had to do. We had to do a lot of transformations that which we have to have it. Then we actually converted those to linear terms. As I said, many times you can be very clever and innovative in converting nonlinear terms in terms of linear. So linearity actually helps you in terms of an optimization and estimation. You are not losing anything. You are just reformulating it. You are posing a different variable and solving for it, right? And which in the classical reaction engineering we have always done. Remember when we did this, like Arrhenius type of equation, we say k exponential e over RT. If you take the log part of it, you say log A, and then you say log A is equal to B plus minus e over RT. Then immediately that all the exponential term is gone, right? So we have always done this in chemical engineering, this thing. So this actually doing all those transformations to make it amenable to solution. So once you have these, and then there are other bounds and blah, blah, blah. Okay, so that's good. Now I'll show you what happens, okay? So this shows you that, okay, other thing I did not discuss it yesterday, but maybe briefly touched it a little bit about the machine learning approaches. So remember, like you can always consider a lot of chains and exactly feed the data. But what you are doing essentially, you are increasing the number of parameters. So you are overfitting it. It's always a good practice to check the number of data points versus the number of parameters. A rule of thumb is that we would always like to have the number of data points at least 3 times than the number of parameters. But data point is not an arbitrary data point. So if you are there in my seminar yesterday, one thing which I was mentioning here is those data points, in some sense, we are assuming that these data points are informative data points. I can put a straight line and then pick up 20 data points from that. This is not informative. That does not give me any new information. So if you have informative data points, then those many number of data points are actually expected to give you a good idea. So this is heuristics, but this is in measure which we use is called Akaike information criteria. This actually trade-off between your improvement in the RMSE, root mean squared value, which will monotonically decrease with your increase of parameters, but this actually penalizes your overfitting. So number of parameters, it will actually overfit. If you overfit it, it will penalize it. So in optimal, so this is the way it actually do that. So k is actually the number of parameters. So you see that how it actually shows up. So this is monotonically improves, but this guy actually plays like a tug of war. So it basically says, no, you are over parameterizing it. So if you see here, with this more theoretically oriented model, you see that this is what we actually get. And what we found here is that over that heuristic model, that SIFS isotherm that we said we updated, it actually gave a 6x reduction in the prediction error overall. So this is how the fit to for that more chemistry oriented model gives it. So it is possible for you to develop it. You may take some time. This took us more than a year actually to develop it, because we are not chemists. We have to go back and forth with the chemists to say, does it make sense, and this is what we are finding, and all of those. And but it actually eventually you can develop, and it can work then. So now what we wanted to do, so this is now coming to your heat of absorption question. So see, as per the model, what it is actually shows up in terms of heat of absorption. So heat of absorption here, over the loading and over different temperatures, we found that it could actually significantly vary that. This is something which has been documented for many, like if you have done work with the solvent based approaches, remember how the solvent approaches like amine, heat of absorption, how it looks like. So I am just showing you for MEA actually. This is monoethanol amine, like how it looks at minus delta H, and this is the loading. These guys will show like this. It actually becomes carb actually, T1, T2, T3 like that. It's a strong function of the loading. So there is nothing called a fixed heat of absorption. The heat of absorption is expected, fundamentally expected to change with respect to your loading and your temperature. Generally we put a constant value, that's for our simplicity. And if you ask somebody to do a calorimetric measurement, my understanding is that there are very few labs in the world that can actually do a calorimetric measurement. You can tell me I'm wrong, but based on many labs that I have interacted, very few labs in the world can actually have these calorimetric measurements for the heat of absorptions for this type of carbon sorbents. Like if you say, okay, I want to sweep it and do the whole thing, there are all kind of things going on, especially when the temperature goes above 100 degree. When water starts evaporating, there are all kind of things starts happening there. So it's challenging, but what we wanted to do is that we wanted to constrain it within some value that which, based on our discussion with the chemist, they said that we are expecting, based on the fundamental reaction that which we are considering here, it should be expected within this range. So this was the constraint, but it looks actually very highly nonlinear. This type of model, what is the advantage of this type of model is that it also gives you more information. Like it basically says how much is amine is getting formed, how much of free CO2 is actually there, how much of species B fractions is all there, so this chemisorption there. So all kind of other things that are actually there, which that heuristic model does not give you the information. So I'm just plotting only few things here, but it gives you the whole chain information, how many species are getting formed, and so on and so forth. Then we wanted to compare these with something called a Hill coefficient model. I'm not sure how many of you are familiar with. It seems like in biological systems, they routinely use it actually for all the biopolymerization reactions and things like that. So they call the Hill coefficient. Based on the data, you can actually estimate what is the chain length. So that is what these researchers, they were actually doing. So they were coming up with, from that Hill coefficient calculation, they are getting a chain length of, it will not give you a integer, it will give you a fraction, that Hill coefficient model. So the idea what we wanted to have is that our detailed model, how different it is compared to the Hill coefficient model, which is well recognized in the literature. And this was something we were holding our breath to see how it compares. And it was interesting that this number is actually very close. For us, it's an integer because it's a chain length. So it's an integer variable for us. So it went to 11, which is really the close value that we are getting from there. I mean, it could have been a couple of things more and less. That gives us some confidence about in terms of what is really happening. This also gives you a lot of idea about what happens to physisorb and then all the physisorb loading and the CO2 fractions and all of those things. So this part is finished here. I just wanted to see anybody has any question for me. Right. So there are two. So if you want to study this is there even in Wikipedia. You can study that. Seems like I'm getting some echo here, right? Is it good now? It seems like some echo. Is it okay? Or I'm good? Okay. I mean, I have no issue, but as long as you guys can hear, it's probably these guys you started. Okay, that's okay. It helps me also in terms of my voice. Okay. So good. So these things are known as information criteria. There are two information criteria that are widely used. One is AIC, and then another is called the Bayesian information criteria, or BIC. These information criteria actually captures the trade-off between the model accuracy and the number of parameters that you have. So the tug of war between the accuracy and a gigantic model parameter, which you may be overfitting, are captured by this one. So this is one of the approaches. Yesterday, what I actually presented in one of these in my presentations about the parameter estimation, that also has got an extended AIC, that machine learning work that I was presenting yesterday during my seminar, that has got an extended use, that which brings in also the covariance estimate of the parameters and directly penalizes with respect to that. So, okay, any other question here for this part of the work? Okay. Yeah, it looked a bit complicated, but do not worry about this one. So it really depends upon the system that you are talking about. Now, the next thing comes there is that in the lab scale, when you develop these isotherm, so Professor Sridhar actually talked about the isotherm parameter estimation, and we discussed that. But the other thing is that isotherm is an equilibrium information. We are interested about getting kinetic limitations and kinetic information, because many times you might have a very good in terms of the equilibrium loading, but that equilibrium will be achieved with a residence time of maybe 5 hours, 1 day, 3 days, or whatever. So the issue that comes there is that you do not have that much of time. As I was saying the other day, like you have only a couple of seconds or minutes. Like many commercial systems has got residence time only a couple of seconds. So kinetics is a very important thing. So if you have a lab scale material, one of the standard way of doing it is to use the TGA data, the thermogravimetric data. This gives you a time series information about the uptake rate. How fast is the CO2 getting loaded? So for this material, this is from the thermogravimetric data, TGA data. and then it basically gives you the loading. So we estimated all our parameters here. So you are seeing this. This is again a parameter estimation. Exactly you can solve it the way that Professor Sridhar actually discussed there. First you do the isotherm model. This should be your next step. So today in our Aspen adsorption workshop, we will just take the parameters from the literature and use it. But this is not the parameter for your MOF, right? You have to establish it. So I'm basically discussing it, what you really need to do for your material. So after you are done with the isotherm model, which we discussed, then the next step is to have the TGA data, and then use the TGA data for getting the kinetic parameters. So we propose some kinetic model. You can come up with a different kinetic model. You notice that this is this kinetic model that which we have over here, that this and this is the driving force between this equilibrium loading. So this equilibrium loading is coming from your isotherm model. It could be a chemistry-based isotherm model, it could be a heuristic isotherm model, but this is coming from isotherm model, and this K came, we are proposing a Arrhenius type of rate equation. See, this is Arrhenius type, right? Which then you estimate this parameter, this parameter, this parameter, and this parameter. And again, it's an optimization problem, and this is how the fit actually looks like. So we saw that this Arrhenius type of model could correctly capture the trend. So this is really your second step. This part, so one thing which you have to always remember here is there are three things here. One is equilibrium, second is the reaction kinetics or adsorption kinetics, and the third is the mass transfer resistance. If you have your adsorbent and then you load it into a fixed bed and you do the breakthrough curve, everything shows up together. You cannot separate them out, because the limitation that it shows is because of kinetics for this type of reaction as well as the mass transfer resistances. So how do you separate them? There's no way you can separate them. This is a challenge actually, and so when you try to fit a model, you are kind of lumping everything up and basically saying, okay, this one parameter is capturing like a catch-all type of thing, right? But here, if you really wanted to do it, this is in a powder form. So it has really got no mass transfer resistances, because these are actually very, very small powder particles that which you are actually considering in a lab scale, and this truly gives you kinetic limitation rather than mass transfer limitations. So that's what you really need to do. That's the second step. Third step is basically that you get those powder form and then you put it in form of a pellets or a spherical particle or whichever is the shape that you are considering for your systems. Like as I was saying the other day, there are all kind of things people are coming up with, like a laminated structure, there's honeycomb type of structure and all of those. But those materials has got a lot of fillers into it, their hydrodynamics is different. So that mass transfer resistance that you have is completely different. Here we do not have a mass transfer resistance. So the third step is for you is using those type of particles in a fixed bed and run breakthrough experiment. Once you run the breakthrough experiment, then that gives you, like this is a model, again I'm probably putting the cart before the horse a bit, but Professor Sridhar will be discussing these equations in more details. But simply thinking, if you have a mass transfer rate like this, so which has got these mass transfer parameters, and then we can consider the internal mass transfer coefficients. These things will be more clear after Professor Sridhar is done with his theory part here, but these are actually a mass transfer model. You can come up with any type of a mass transfer model, but what it does is that it will give you a bunch of parameters also here. So this is really the next step, that how you estimate those parameters step by step actually. So once you have that, you take the breakthrough data and then what you do here is this is how the breakthrough looks like for that particular MOF. So what I described here so far, first is isotherm model development for one type of MOF. The next step that you need to do is the kinetic model development. Then you put it in the shape that you would like it to be, like a spherical particle of 50 micron or 100 micron or whatever. For that, you put it in a lab scale reactor, and there you measure the breakthrough curve, and then from there you have estimate the mass transfer related parameters. So this is the step by which it will go. Does it tell you the true story yet? No, because this measurement, notice that I said this breakthrough curve is generated from a lab scale system. When you put these materials in a commercial scale, so lab scale is like 1 inch diameter, right? And then when you go to the commercial scale, it's like 5 meter diameter or whatever. It's actually can become giving you a lot of other uncertainties. That's a scale-up problem, and we can have a discussion later on. So there are additional parameters that needs to be considered. But a lot of those bigger size, your hydrodynamic model becomes very important because it may actually channelize from one side, the distribution becomes very important, and so on. So hydrodynamic model, distribution, scale-up uncertainty, radial variations, all of those come into picture. Again, some of the papers I will be citing, we have actually looked into that. So because of the time, I will not go over that, but this is what I wanted to tell you this one, okay? So that is for both the MOFs. So that one, that, and like this is this one. So you see how the breakthrough curve actually looks like, right? And I think yesterday you guys were discussing about, see, this is a breakthrough curve, like looks like this, right? But see, this guy is breakthrough curve actually. So which I was saying that, see, this is a 2 steps. So it actually showed up first breakthrough, then it has second breakthrough. So it can be all kind of complicated things that you can see, and then the idea is, can your model really predict all of those things? And we found it was reasonably okay with us, with these models to capture that, okay? So in the concluding remarks, I'll first say that I have these papers here. So these are all published. Some of them are actually very recent, like this chemistry model is last year, towards the end of last year. Then these double step shape things is also last year, that which you have these. And then this one actually is 2 years back, the diamine appended MOF. So a lot of details are here that which I did not discuss as part of this, but this has got, also goes all the way up to the scale up problems, also goes into the economic calculation. So if you are interested on this, all these things starts with a fundamental isotherm, then go to the kinetic model, then goes to the mass transfer model, then scale up to a commercial scale, then integrate that with a power plant model, and then do an overall economic calculations. So this is that, those papers has got all those details. So if you want to see any of those things. But what I wanted to say is that the isotherm models can be complicated, and but it may be, you may be interested, as a researchers, we are always love these challenging problems, right? That saying, okay, there may be a very complicated reaction mechanism inside the cage. There is no way I can figure out how the chains are propagating. Can a mathematical model really represent those ones? But it turns out that yes, we could actually. Of course, there are more data would be needed, but this could be, this type of model can give you more predictive accuracy, because those are all fundamental models. Those are all constraining to the thermodynamics of this type of a systems. Kinetic models should be based on TGA parameter. Mass transfer resistances can be based on the breakthrough data. And I will say, check out these papers for more details here. Okay, so that is all that I had for here, and let me know any questions.
In my own way, I'm thinking regarding absorption and distortion. I'm trying to understand how the phenomena is taking place.
for example, you see here some kind of cylindrical solid material, adsorption material, which has more porous. Say, for example, say 100 numbers of 100 cylindrical small nanoporous of the, and they can say area also, let's assume that say some size this much diameter is there. With respect to temperature, so when gas passing through that absorption material, again the temperature gradient will be there from
Right.
to middle or this side there.
Right.
Again the capacity of capturing that CO2 naturally varying from this point to this point.
Right,
Very
right,
different.
right.
When we are talking about that stage, first stage and two stage, like that's happening. Again, for example, you see, suppose it will not be there, disruptions, once it's absorption taking place and disruption taking place, it will not become to zero.
Correct.
Sometimes it will be the 20, 100
Correct.
to 20 or 100 to 30, 100 to
Correct.
40, like that will vary.
Absolutely.
So this, how will it be saved throughout the surface, or this kind of stuff, so that anybody has applied to their mind, modeling this kind of problems.
Yeah, this is what I wrote is that's the concept of the cyclic steady state. So all our papers, like all the results here, are under cyclic steady state. So these papers, if you read it, this will actually tell you that how you establish cyclic steady state. I will also show you in Aspen AdSim, because of the time, we'll have the bandwidth to cover it as part of this class. But once you really be familiar with Aspen AdSim, AdSim has the capability to simulate those things. So you simulate, and it will keep cycling till it achieves the cyclic steady state. That basically means is what I wrote there, where you ended the desorption, that is where the adsorption starts. So the subsequent cycles, there is a tolerance actually. The end of desorption cycle and beginning of adsorption cycle, when those relative differences is below some tolerances, it will say, yes, we have reached the cyclic steady state. Run some of these codes there. It's actually in their example file. So I will go over that in the afternoon. But there is actually massive amount of work. This is one of the notoriously difficult dynamic optimization problem. If you really are interested in doing a dynamic optimization, then the way it is done in Aspen Tech is perhaps take you a lot of time to do that. I will suggest, if you are very familiar with Python, then I will suggest Professor Lorenz Bigler from CMU, and you can start with PSA, and then you say CSS, and these two hits will give you that. He has worked on this area for quite some time. This is IPOpt is his software actually, that which we use. This is behind the scene actually is one of the most powerful NLP solver that actually behind the scene many other software actually uses it, and he has worked extensively on this area. But that actually just put that equation directly as a constant, and that is what you need for optimization of those things. So we have done also optimization, but yeah, this is a discussion for a later point. If you're trying to use this optimization in Aspen, you have to keep it limited to very few variables. Because the optimizer in Aspen does not actually see the Hessian information and the Jacobian informations from the lower scale model. So with this work, actually, you can see this, utilize the Hessian information. So you can, even the gigantic models can actually be solved as optimized. This is the code that which we always use for many of the optimization that we use here. So this is all Python, and it is very nicely coded in Python also.
Sir, why don't we wait for 100% desorption? Is it uneconomic?
Oh, it's actually I will suggest that you actually, when you become familiar with Aspen AdSim, you try it, and you will see how much time it will take. Because you have the driving force keep going down, 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 down. You will see that up to certain adsorption you will quickly get, and then it is slowly getting to that one. Maybe the top portion will desorb, but the bottom portion will not desorb.
It's like an asymptotic curve.
Correct. So you do not want to wait forever. So there is an economics there, because more time you wait for desorption. Go back to my discussion yesterday about the total number of bed. you will require much more number of bits. So basically the idea there is, it's ultimately is the economics that matters, like total number of bits, your capital cost will go up. So that's an optimization problem. So all our papers, like if you look into all of these papers, this has got considered the desorption time as an optimization variable. Yeah. Okay, other questions? Is there any question online? I guess. Okay, so far, and you have.
When searching for minima during the parameter estimation, there is no unimodal. We get different solutions for different parameters, and the errors look very similar. From what I understand, Aspen just knows the mathematics of it, but doesn't go after the physical significance of those parameters. So, how do we actually select when we are not sure about what kind of parameters are should be there?
Bound the optimization variable in variables in the expected range. This is absolutely crucial. So for what it basically means is there is a low limit and there is an upper limit for every parameter that you consider. So upper limit here. This will give you some of the physical bound. How do you get it? This is based on the literature. So for example, if you say mass transfer coefficients, I actually study like 100 papers and say this is the typical range I get. I'll do that. Second is bring in additional constraint equation. This is the same thing which I said, that for example for those other things, that where we had the constraints there that which we considered for the heat of reaction, the isostatic heat of adsorption. If you do not consider this, there are actually many parameters that become acceptable. But when you bound it actually, that immediately constrains it to saying, no, this is not acceptable actually. This is the issue with the machine learning. There is no unique solution to this. You start with a one parameter guess of initial parameters, it will solve to that value, and then because those parameters are meaningless, right, if you are doing a machine learning. But for chemical engineering application, those parameters are not meaningless. We know what those parameters are expected to be. Like if I know mass transfer coefficients, we know the fastest mass transfer coefficient that could actually happen. What is the slowest mass transfer coefficient that could happen? So all those things, yeah, please, we need to bound those variables. We're probably running out of time, so please come in. So it's Professor Sridhar's turn now, and then we can take any additional questions after. We'll be all here, and afternoon we'll continue. Okay.
Thank you. Yep. Just sitting here. You want one PC? Uh, so welcome back to the tutorial 2. So there is one small problem we will solve in Aspen adsorption, and we start from where we left in the last tutorial. So in last tutorial we discussed about how to estimate the isotherm parameters, and by using the MATLAB code we used LSQ curve fit. My voice is not audible? Column. Okay, I will be loud. So in this problem we will look into the CO2 N2, that is a binary component system in the ratio of 15:85. Okay, this is customized the components we made, but in real flue gas we will have other gas molecules also along with CO2 and N2. And the adsorbent that we select here is zeolite 13X, that is one of the zeolite, okay, that is very good for CO2 separation from the flue gas. And we make couple of assumptions. Once we start building the system, I will show what are the assumptions we are making and how each equation that we discussed in our previous previous lecture regarding the modeling of the carbon dioxide capture system, how that is related to the Aspen adsorption software, how we are building each equation one by one to solve this adsorption process. Again, there are two important informations we need, that is one of the mass source and another one is the heat source, what is the heat of adsorption and also what is the adsorption amount. So okay, fine. So how do we get the adsorption amount? Which term will solve this information?
They both, you can get 3 days. How was it?
So heat source we will get from heat of adsorption. How do we get the mass source? Okay, the last term in the left hand side, that is 1 minus epsilon b by epsilon b rho p dou q by dou t, okay, that is our mass source term. So the q is the term that we will get from the adsorption equilibrium. Okay, the adsorption isotherm model that we fitted, okay, that model we will use to get that information in the fluid phase material balance. So this is our problem statement for the Aspen adsorption, that flue gas contains CO2 and N2, okay, that is a binary component in the ratio of 15:85 at 25 degrees Celsius and 1 bar pressure. Okay, CO2 is to be adsorbed using zeolite 13X. Okay. So we will see how to get the breakthrough curves for this system, okay, by using Aspen adsorption. So when we are trying to model one adsorption process, we need to understand various properties, various adsorbent properties and also the thermophysical properties of the system. So this information is obtained from the article given here. Okay, you can go through this article. All the properties, we need adsorbent specific heat capacity. Okay, that is the term Cps present in the energy balance equation of the solid phase. Okay, and we need fluid viscosity. Why do we need fluid viscosity? Fluid in the sense the gas, the feed gas that we are sending. In the momentum balance, we have the in Ergun equation, you might have seen the viscous term, right, where we use this fluid viscosity. and we have molecular diffusivity that is required, that is for the axial dispersion that is required in the mass balance. Then we need the feed temperature, at what temperature that we are feeding the gas, source gas, and universal gas constant, and we need specific heat capacity of the CO2 and N2. Okay, this is for the energy balance of what? Gas phase. Okay, we have two energy balance equations we discussed, right? Gas and the solid. Then we need thermal conductivity, that is very important property for the thermal conduction term in the energy balance equation. Okay, we need the thermal conductivity of the adsorbent. The specific surface area we need, I will show in the coming slides where do we need this term, and we need the dimensions of the bed. Okay, what is the length and what is the inner radius and outer radius of the column, what is the design. You can tune these terms, okay, the bed length and the column radius to get the optimal design also. For now we will consider these values from the paper. Then we need bed void is. What is bed void is? So when we are packing the pellets, okay, there is a space, the void that is present in the bed, okay, that is the bed void is. Okay, then what is particle void is? Pores, yeah, these pellets or particles, they contain these voids, right, inside, that is a particle void is. Okay, and particle radius, what is the radius of that particle we are packing, and also the density of the solid particle and density of the column, the whole the bed, okay, column in the sense. And density of the wall, what type of wall we are using for packing this material, and effective heat conduction coefficient. Effective heat conduction actually gives us the information of both gas and also the solid, okay, that is present inside the bed. Then thermal conductivity of the wall and heat of adsorption and heat transfer coefficient. Okay, this is the outer heat transfer coefficient, how the heat that is going out by the convection. So this information is required if you would like to simulate one packed bed, okay, to estimate either performance metrics or the breakthrough curve. Okay. So now we need another important property, that is adsorption isotherm parameters. Okay, yesterday we discussed how to estimate the adsorption isotherm parameters. Okay, if we have adsorption equilibrium data, okay, we will fit the model, whichever is a suitable model. We used dual site Langmuir model, okay, to estimate these parameters. So this is how we see this dual site Langmuir model in our literature. Okay, this is how the Aspen interprets this model. If we convert, both are same. Okay, the QSP, yeah, this is a QM2. Okay, that is a coefficient, and also B2, this is a coefficient. B we can represent as in terms of K multiplied by exponential of E by RT. Okay, if you check in the Aspen adsorption help or the manual, okay, this is how Aspen reads this dual site Langmuir model. So we converted these parameters into this form. We will use the data, okay, this data, mainly the CO2 and N2 information, around 8 parameters. Okay, we will use to pass the adsorption equilibrium information to the solver. Yeah, and also we have mass transfer coefficient. Where do we use mass transfer coefficient? Yeah, we need kinetic model, right? Equilibrium is good, we have equilibrium information, we need kinetic information also. Okay, we will use simple LDF model where K is the mass transfer coefficient. Okay, now you can start doing with me, you can start working, building the Aspen adsorption model. Okay, there are slides, one by one we will move on and I will explain, and you can start building your model. We will start with defining the component and the property model. Okay, in our previous tutorial 1, okay, you know how to add the components in the Aspen, right? We will start with that. So this is our everyone, you can open your Aspen adsorption software. So go to this Windows logo, okay, here you can either type Aspen adsorption, okay, that will open the Aspen software for you. So this is how our environment looks like. This is where the flow sheet will be drawn, okay, the packet bed, and also what are the feed that is coming in, what are the outputs that are going. Okay, at the bottom, in case if you cannot see the symbols, okay, at the top in the view button you can check whether the model libraries are selected or not. Okay, in the view option there is a model library should be selected, then only you can see the dynamics, okay, cyclic steady state, liquid ion exchange, all those options you can see. So this is a simulation where we can have multiple options, all the items that we can select here. One is the component list, and also we have variables, global variables, and the flow sheet and the local library. Okay, in the component list we can find, we can add what are the components. What are our components? CO2 N2. Okay, simple, that's it. We can add our CO. If you click on this component list, just everyone on the same page, right? You could open the software. Okay, then double click on this component list. It will take you to the contents of component list where add components, configure properties, and the default option is there. Okay, click on configure properties. So Aspen has this database of all the various components, gas molecules, okay, where you need to select the CO2 N2. So then select the use adsorption property system and click on edit using Aspen properties. So it will take you to the Aspen properties window, okay, where you can add the CO2 N2 properties. So this is how the Aspen components, okay, components and the specifications screen will look like. Okay, is it open? Good. Here you can type CO2 and N2. Or else carbon dioxide or nitrogen, okay, you can select. Type CO2 and N2 here, that means it will select the both the components, gas molecules. If you cannot find, then you can click on this find button, okay, it will open the window where all the molecules you can select whatever the one you need. The CO2 that you can directly check like this, okay, if it is matching you will directly find the carbon dioxide molecule with the database, okay, what are the properties that are required for the CO2, then N2. Okay, these are the two gas molecules we need for solving this system. should we move to the next step? Did you select the both molecules or not? Good. Okay, then click next here. We need to give what type of model or what type of method we will be using for the gas molecules. We will select the ideal gas method. Okay, since we are using the system at 1 bar and 298 Kelvin, we can go for the ideal method. Okay, if you type ideal here, okay, you can directly select the ideal method. Then again click next. So it will show the required input is complete. Okay, either you can run the property analysis, okay, and minimize this window. Okay, that means the component addition of the components to the system have been completed. You can click OK here and check what are the components have been added. Now come back to the Aspen adsorption window. Okay, so this funnel symbol is where we are adding the components. Okay, and this is what the Aspen adsorption logo looks like. Now come back to your Aspen adsorption window. Okay, if it asks you to save the properties that you uploaded in the Aspen components, just save those properties. Okay, then come back to the Aspen adsorption. So you can check whether the added components are correct or not. Okay, you can click on this default option. Here it will show what are the available components we have. It is like a small database we created. We need CO2 and N2. Okay, if you click on this double arrow, okay, these CO2 and N2 molecules will be selected for the calculation. Please do it. Just click on that double arrow. Okay. Sorry. This one after the components. Click on configure properties. Yeah. Okay, go to the edit Aspen properties.
Done.
But we don't see your properties, sorry, the components in the default. It's supposed to be open, right?
I have after adding those components, I have saved and cut the window.
Okay. Then click on next.
Okay.
It will take you to the method which we will be using. You didn't select the method for the components, right? That is also important.
Ideal.
Yeah, ideal. Okay, click on next.
I haven't clicked next this way.
Okay. Or you can run and save. The property analysis it will do. Okay, and it will save.
This also, yeah. After that,
Click run.
click run. Achha, I didn't run. Yes.
Okay.
Now it will work, right?
Yeah, close it. Save. Yeah, save the changes. Okay. Go to the default. Yeah, it was selected.
I just follow you, sir, because, so that I will understand more. When I am following your things,
No,
I
I-
am getting more.
Do it. No. You can do it, no?
Run the system, I am not working.
No, slowly we are going. That's why.
Where should the components show? said we cannot go here, no?
So we will go to the next step. Once you select the components, it's supposed to show in the available component list. Okay, then we will select those two components for our calculation. You can click them like this, okay, so that we can select both the components into the available components into the components for the calculation. Then click OK. Okay, this step is done. So we assigned what are the components that are required or what is the source gas, okay, that we will be using. So next step is to build the flow sheet. So here at the bottom, I guess all of you can see the model libraries. Okay, we need a bed, gas bed that we can select, and also we need a feed, gas feed, okay, and also the gas product. What is the product that is coming, what is the gas that is going in, okay, and what is the process that is happening, that is a bed. Okay. So first click on this gas feed symbol, okay, and drop it here. You can drag, once click on the symbol, drag it and drop it in the flow sheet. Okay, similarly we can click on this gas bed, drag it, drop it in the blank flow sheet. Then we need gas product, click, drag, drop. Okay, is this enough? Can we run? No, we cannot. We need to connect the feed to the bed, okay, and also the product to the gas product symbol. Okay, we need a connections for the gas flow. So in the drop down option here, you can see at the corner there is a connection logo, right? Just click on here, it will open the connection, gas material connections, okay, and also the control signal. We will select gas material connection, okay, this is a gas phase. We will select the gas material connection. Again, click on that connection. Okay, once you drag it to this flow sheet, you will see these nice blue arrows, right? Okay, drop it here and connect it with the other end. Okay, one is source, another one is destination end. So click on this source, drag it and yeah, connect it to the destination. Okay, this completes the feed, how the feed is going into the bed. Okay, similarly how the product is going out. Okay, you need to connect another gas material connection from the other end of the bed to the product.
Bottom palette is not coming.
Go to the view button, view, click on view, select the model libraries. So in case if you are having difficulty, just right click on this thing. Okay, it will ask you what is your source. Okay, then here you need to give the source. Still we will delete this one. This is unnecessary. Okay, then similarly if you want the destination, okay, is this product? Okay. So a lot of so all of you could able to connect, right? Okay. So once the flow sheet is ready, we will start assigning the components. What are the components that we are giving in the feed, and what are the properties of the bed, and also what are the ratios or components that we are expecting in the product. Okay, if you double click on this feed symbol, if you double click on the feed symbol, it will open the configuration, okay, of the block 1. Okay, you can name this as a feed also, and in the block we have a specify option, okay, where the components can be specified. If you click on the specify, it will ask for the flow rate and the composition of the CO2 N2, and what is the temperature and what is the pressure. Okay. So we have the information of composition. It is 15:85. Let's take 0.15. Okay, and nitrogen information of 85%. Okay, and the temperature is at 298 Kelvin, 25 degrees. Okay, and the pressure we are taking 1 bar. Okay. Good. What happened?
That icon is not coming, so adsorption.
So this is, yeah, this is Aspen. Okay, if you enter the feed specifications, then click on the product specifications or the bed specifications. Okay, as mentioned in the slides, you can enter one by one.
In the field specification, should we that variable specs, right? So that should we actually make it fixed or something like that?
Yeah, we for temperature, pressure, and the mole fraction are fixed. Okay, because we know the values exactly.
The feed also flow is fixed.
Flow rate, we have enough information to solve those equations, right? Okay, so this we can leave free. Automatically, it would change according to the calculations.
Okay, no, I thought of the product side we can leave it free and
Yeah, we can leave it free.
feed side we
Yeah,
can, because like
you can try that. You can experiment on that. Is fine. But I will show at the end bottom there is one symbol, right? The symbol, yeah, that is denoting either over specification or under specification of the parameters. It has to be the green square. That means all the properties are specified properly exactly. Okay? If it is down arrow, red arrow, under specification, it requires some other extra property to solve the equation. Yeah, click OK. Now it's good. Close it. Wait. Okay, close it. Click yes. Yeah. Okay. Yeah. Now click on default. Okay, now you got both, right? Select both of them.
Interparticle voidage is bed voidage, right?
Bed voidage, yes.
Intraparticle voidage is this particle voidage.
Yeah. Okay, click OK. Yeah. Now Go to the view option. Click model libraries. It was not selected. Yeah. So the tutorial, all the slides have been shared. So don't wait for me. You can start building one by one, starting with the feed and the bed and to the product.
Taking such low value.
So can you repeat the question? So online participants, in case if you are having any doubt, please you can ask me now. Yeah, please go on.
Yeah, the five you had said in the slides need access permission. So I've sent an email asking for access.
Oh, okay. Yesterday I sent you the tutorial 2 slides. You can go through them for now. I will check the permissions in the meantime. Yeah. The same
Thanks.
slides which we were used yesterday are and today's are same. Yeah, you can go through them.
Okay, thank you.
Okay, once the specifications are done for the feed, okay, you can click on the bed specifications. Once you double click on the bed, okay, you will see this window, the configuration of the bed. which contains adsorbent layer. How many layers are there? We are using only one single layer. Okay, and what type of bed is this? Vertical, and also what is the dimension we are solving? It is a one dimensional problem. Okay, there is no heat exchanger in the bed. Okay, if you want, you can add the heat exchanger. Why do we need heat exchanger in this case? For the regeneration, we may need to supply the heat. Okay, that will be one of the useful step. So then you can either click on configure or double click on that bed, the cross symbol you see, right? There also you can double click on it. It will take you to this window. Okay, here we have multiple options. All the equations which we discussed in lecture 10, okay, mass balance, momentum balance, and also the energy balance equations, and what are the specifications of the bed. Everything we need to connect, and we need to enter all the property information here. Okay, it is starting with the general option where which type of scheme that is using here and what are the nodes. You can modify if you want to, you can increase the number of nodes, and the discretization method should be mentioned here. Now moving to the material and momentum balance, okay, either whether it is only the convection or dispersion also we would like to solve. Okay, convection, okay, the convection term is this one, del dot CUC, okay, and this is a dispersion term. So if we are selecting convection with dispersion, that means we are considering both the terms. Okay, we will go with convection with estimated dispersion. We know the value of the dispersion from the literature. Okay, that is what we are selecting here. So momentum balance assumption, how do we estimate the pressure? We have a Ergun equation. Okay, I hope you remember the Ergun equation we discussed in last lecture. We will select the Ergun equation here. Good. Start following. Yesterday slides were there, right? One by one, step by step has been given in this. Okay, you don't need to wait for me. The step by step procedure has been given in the slides of the tutorial 2. Start building. ఉంది కొంచెం పైకి స్క్రోల్ చేయండి. So once momentum balance and the material have been selected, we can move to the next step, that is a kinetic model. Okay, linear driving force model we are selecting. Everything is by default is selected the LDF model, okay, form of lumped resistance model, that is a linear selected here. Okay, you don't need to worry about changing it. This is fine. Now move to the isotherm, click on isotherm option. Okay, here we can select what type of adsorption equilibrium model that we would like to use. We have multiple adsorption isotherm models. If you click on this drop down option, okay, from top you can see BET multi-layer and dual layer BET. There are multiple options we can see. There are how many types of adsorption isotherm models available. So we will select dual site Langmuir. Okay, we will click on dual site Langmuir. That it goes to the next step, that is isotherm dependency. So we will use the partial pressure of the gas. Okay, once we select the isotherm, we will move to the energy balance. First we will see how the breakthrough curve looks like for the isotherm system. Okay, isothermal system breakthrough we will compare later with non-isothermal. Okay, so there is no reaction happening, so we will leave this option. And now if you click on the specify, okay, you will see all the properties that you need to provide for the solver to give you this breakthrough curve. It is starting with height of the adsorbent layer, which is 1 meter. Okay, then we have the internal diameter of the bed. That is 0.1445 meter. Then we have interparticle voidage 0.41 meter cube per meter cube of the bed. Then intraparticle voidage, which is 0.35. Then rho s, that is the bulk solid density of the adsorbent, that is provided as 1130 kg per meter cube. Then what is the particle size? Okay, radius of the particle, which is specified in mm, which is 0.75. Then we need to provide what is the mass transfer coefficient for the CO2 and as well as for the nitrogen, which are 110 and 5 1/2. Okay, then we selected convection with estimated dispersion. So this option, the molecular diffusivity of the CO2 and N2 should be provided, which are around 1.6 e 10 power minus 5. Now we left with adsorption isotherm model parameters IP1 to the IP8 for CO2 and the N2. You can use the table which provided in the slides. So this completes the properties that are required for the adsorbent bed. We can close this and click on preset initials. So what is the CO2 that is present in the bed initially? That is 0, and nitrogen, we will consider this as 1. Okay, and close that. We can click on initialize. That will set the properties of the bed. Okay, now you can go to the result and check whether the properties that we have initialized are assigned correctly or not. Okay, the Y from the node 1, that is the entrance of the bed to the exit of the bed. Okay, what is the amount of CO2 and what is the amount of N2 that is present? We assigned at time 0, okay, as 0 moles of the CO2 and N2 as the 1%. So now the feed and adsorbent bed information has been provided. Now double click on the product option and specify the product properties. Okay. So we want nitrogen at the end, at the exit, okay, and CO2 to be adsorbed in the bed. We will select this 0 and 1, and there will be a pressure drop in the system. Okay, we will consider a very low pressure drop, 0.998. So all the specifications have been given. Okay, now we need to initialize the bed and run the simulation. Okay, from 0 seconds to the 500 seconds to see how the CO2 concentration that is coming out of the bed. So anyone is having trouble in giving the specifications? So once all the properties have been specified, okay, we can go to the flow sheet option, okay, and click on check and initial. Okay, it will initialize the entire the process. Just click on S. Okay, in the messages box at the bottom, you can see are there any errors in the various steps that we have followed so far. Okay, it should supposed to show the no errors were found. So to get the figure, now go to the top toolbar and click on the new form. Okay, and we will create one profile for the breakthrough curve. Okay, so we need to plot this for the mole fractions of the carbon dioxide and the nitrogen. Now click on this product option and go to the results. The drag Y forward CO2 and Y forward N2, these are the mole fraction values at the exit of the bed. If you drag these two mole fractions, okay, it will create one profile, okay, the profile at the exit of the bed after the process from the time t equals to 0. So you can control up to what time this process should happen. Okay, there is this play symbol at the top. If you click on that symbol, where you can give the time limit up to what time you can, at what point you need to stop this process. We can give some 100 seconds or the 500 seconds, or if you transfer multiple hours, that also can be specified here. Okay, we will specify.
Where you get this breakthrough curve?
Yeah, sure. So to get the profile, you can go to this new form option that is in the toolbar. Okay, if you click on that, here it will ask what type of profile you need. We need a plot. Okay, you can give the name of the plot. We named it as breakthrough. Then it will create one nice plot. Okay, something similar to this. So however, the dependent variables we need to mention. What are the dependent variables we need with respect to time? Okay, our dependent variables are the mole fractions at the exit of the bed. Okay, so you can double click on the product option and go to the results. Okay, and select Y forward CO2 and Y forward N2, which are the mole fractions at the exit of the bed. Okay, you can drag these two options to the y-axis of your profile plot. Okay, that's how we can create the breakthrough curve. So then, if you click on this run option, you can select up to what point this simulation should run. Okay, for 500 seconds we select it. So this is a dynamic simulation. Okay, once everything is good, we can click on the play, that is the run option. Okay, to see how the profile, the breakthrough profile that is changing, you see this message of run has been completed. You can zoom full. Okay. So this green, green profile is for the CO2 and this is for the nitrogen. Okay, at the end after the saturation, both the CO2 and N2 which are present in the feed coming out. What is the feed composition? 85% of the nitrogen, 15% of the CO2. If you observe around at 250, more than after the 250, you see the same composition of the gas coming out. What that means? Bed is saturated. Okay, if you want both of them in same plot, I mean you need same two scales for the y-axis, you can right click on the properties of this plot and go to the axis map. If you click one for each and apply, it will create two y-axis where you can see how you can zoom it, how the variation of the CO2 with respect to time and N2 with respect to time. So this is a breakthrough curve for CO2 N2 on zeolite 13x bed. Okay everyone, we will take a break and we'll meet at 1 o'clock and continue this tutorial with Dr. Debanshu's tutorial, okay? And we'll see how non-isothermal also work and we'll compare both the breakthrough curves. Okay, if you get the breakthrough curve for isothermal, try non-isothermal also. If you are getting any error, then let me know.
Still stuck at the old thing.
Yeah, we will solve it now.
Okay, I think she had some questions. Huh?
Getting the graph.
Oh, she will take care of it. Okay, good, good, good. So, help me to ensure it does not fall off. All right, okay. So, this guy, the one below, yeah, the one below. And then for the ACM file, the other one. This looks good to me. Yeah, this looks good to me. Okay, I'll jump here. And yeah, so from here backwards. Yeah, so it'll be there. And if we open the ACM file, that one. Okay.
Adsorption or custom modeler?
No, it's been that same. Yeah, that's okay. I just modified it. Yeah. Okay, that is good. And you put it on the folder.
No, this folder is open.
Okay. Okay, it's already open. That makes sense. Yeah. So I have to share my presentation, right? So let's go to share my presentation and then, or share the screen. Is it okay? All right, so I'm guessing everybody got the breakthrough curve, and if you don't, Professor Sridhar is going around and will help you. And let me know if you need anything here. One thing, when I was sitting with some of you here, I wanted to tell you one thing that you need to look into is that when you look into ACM, say you have run it up to 0 to 500. If you click run again, it will go on from 500 onwards. That's not what you want. If you just want to recreate it, you have to fly back to time equal to 0 to do everything. So this is like my the thing that I'll be suggesting. I'll be doing actually a bunch of steps, and I will say, okay, run it back again. So when we say run it back again, that basically mean is that you need to come back to time equal to 0. So how do you come back to time equal to 0? So you come here to the screen. My screen is getting shared, right, online? Okay, good. So you double click onto this and you click onto configure, and then you say initialize. Okay, so it says, do you wish to continue? And you say yes. It will come here. After that, you should first do the initialization, because just flying back does not reset the time in Aspen. You have to, once you do the initialization, if I do initialization, it reset the time to 0. Now when I go to dynamic, it will start from 0. So always look into the system over here, right? Another thing which I would like you to really think about and bring your attention here is that when it is starting back, so what are we trying to do here? So let's understand this one. So this is basically for all the time derivative it is basically saying that I want an initial condition, because these are initial value problem. So I want the initial condition. What are those initial conditions? So that is what Professor Sridhar actually went over, but I would like to ensure that I reinstate that one. So if you want to see by default what is the initial condition, you already assume that one. So what do we assume there? Okay, so this is this guy. This is the initial. So you say initial, rate initial. You do not have these two guys. I have opened a non-isothermal model, so I see these. But look into, please open your model and then click on preset and initial to understand that these are considering initial and these are rate initial. So this is by default, it is saying the first node CO2 is equal to 0 and this is actually 1. It is also saying the velocity in the first node is this guy. I'm not sure any of you looked into it, but that is what Aspen has already taken for you. Okay. Then it is basically saying the CO2 loading and the nitrogen loading is already at these two values. Can anybody remember what is the difference between initial and rate initial? So both are time derivative. So remember, if it will show you initial or rate initial, that means it has a time derivative. All other type of variables will either show up as a free variable or a fixed variable. So all algebraic variables will show up as either free variable or a fixed variable. But this is only for the time derivative. And notice that Aspen is only picking up here the time derivatives. So this is in some sense telling you, if you do not understand really, they're saying, okay, what are the differential variables? And we are confused because I'm not really looking at the equation. This is the way for you to understand it, that these are the time derivatives. So initial is basically, if I'm writing a derivative, let's say if I'm writing dy dt equal to f of y x theta t, so initial is initial means I just provide the value at y at t equal to 0, right, equal to something. I just provide that, I just specified it. So in some sense, even though it has a value of 0 and 1 and all of that, in some sense we have provided that value. Now, when you have these as a rate initial, then what it does is that it dy dt equal to 0, this is the equation it solves. And by solving that, whatever value, it's a solution from this equation generates the initial value of y. And Aspen can take mixed up. So you can say, oh, these are rate initial, these are initial and all of that, but be careful. If you say I am actually starting with something like, for example, if I'm actually going here in the first node and I basically say, okay, I want to declare it as an initial value, right? It's fine. You see, always look into the green thing here. First node CO2 loading and whatever is the first node CO2 load, nitrogen loading and whatever, it has no issue with respect to doing this, because it's looking for a specification. So by default it will take something. Be careful about it, because this is the value at which it is starting with. Okay, this is the one point I wanted to mention as part of this thing, that be careful about it. When you do this and you say, I want to initialize it, so basically it is saying that this action will set all nodes to equal the first node values. Do you wish to continue? So what does that mean? That basically say, if I say yes or good, it is basically saying I just provided the value for the first node. Notice here the first node. But this time derivative, this is a PDE. So it needs the value for all node. But you just provided it only for the first node. So it is asking you, do you want me to load it for all nodes here? And you can say no, and what you can do is you can run a script. Like many cases we do run a script actually. So that script will automatically overwrite it, and that if you want to run your own code for achieving the cyclic steady state, that is what you have to do. Because as I said, that cyclic steady state is the end of desorption profile must be the beginning of or at t equal to 0 for the adsorption profile in the subsequent cycle. So how do you transfer everything from this end of the desorption to adsorption? This script will not do it. This is not how it is actually generated. In that case, you have to write the equations and basically say transfer all the things from here to the other one. So just be careful about this one. This is by default, it's okay, but otherwise you must copy it. There are other ways to actually copy the profiles, but we'll talk about that later. But this is a point I wanted to clarify everybody's mind. So it is basically saying all node in the gas phase, I'm setting these to 0 because for CO2, and for nitrogen I'm setting this to 1. Velocity everywhere I'm setting to these values. This CO2 value I am setting to this, which is no loading, and nitrogen also I'm setting it to 0, and then we'll talk about other stuff later on. Is this clear to all of you guys? This is an important point I wanted to highlight. Okay. Now the next thing we wanted to do is that if we are all comfortable now, we like to go to converting these to a non-isothermal model. So for doing that, let's go to the, I would suggest that the file that you have created, right, keep it separately. That is an isothermal model. And now modify this to a new file, do a save as a non-isothermal model, and once you have done that, let's click this option called non-isothermal with solid conduction. Why we do that, we'll talk about that in a moment. So if you go there and select, it will give you a bunch of options. Once you do that, you will see and then click specify. When you click specify, you will see that these boxes over here, let me get the pointer here. These boxes below, that from CP to up to AP, these values you need to populate here. So where from I am getting these numbers? These numbers are coming from this slide, slide number 26. So you guys have the slide number 26, that which Professor Sridhar actually presented there. You have all the specifications. I simply copied it from there. So I'll keep this open. Once you enter that, I will discuss about a couple of other things. Okay, energy balance, non-isothermal with solid conduction. Look at the setting here and then numbers over here. And then if anybody has any question, let me know. You have the slide 26, right? Yeah, if you have that. Did we share the presentation today with everybody? Like your slides, everybody has that, right? You can share my slides also, that would be good. Yeah. Probably right now not so much needed, but I wanted to see slide 26 they have access to, because the specifications are there. Okay, yeah, and sometime share my slides also. So if you run into any trouble, just raise your hand, please. Yeah, don't yet run. We'll talk about a couple of things and then we can go from there. Yeah, all those you can just use that numbers, or those that I got from slide 26.
No temperature with time. This is not supposed to be 298.15 volt. Where is the heat generated? Electro curve is coming.
Yeah. Yeah, we'll talk about that actually. So
now there is a problem. You see, this is fixed. I don't think in a non-isothermal simulation outlet temperature should be fixed. If I make it free or initial,
no,
then
no, it cannot actually. So I will tell you what that is actually. I'll probably discuss that with others as well.
Otherwise, it seems there are redundant constraints. Otherwise, it is adiabatic. Initial temperature is specified, so final temperature should not be specified as.
No, it should not be. Actually, 3D bursts does not mean that. So I will tell you.
How will it solve the energy equation? It will become redundant.
No, it is not. So the reverse temperature is, if there is a reverse flow, it is saying, tell me what temperature to use. In that case, it does not know what the steam.
In case of reverse flow. Still, my temperature is not increasing. There should be heat generation.
Yeah, let's see.
Decreasing 0.01 amount.
Yeah, we'll run the code and see how it actually probably looks like. So once you do that, I think now everybody is comfortable to generate the breakthrough curve. I think I just suggested to do that, and then we'll discuss about a couple of things here. Where is that? Huh. I just cannot see the cursor here. The mouse, I just cannot see it actually. But then so it's had to do the escape here. It now came back. Okay. Okay. Yeah. Double escape. Oh, double escape. Okay. Yeah. Thank you. Okay. All right. Huh?
You don't need to make it slideshow. Just keep it like this.
Okay. Everybody can see it, right? Okay. Yeah. I was just saying for better visibility. Now, once you do that, the first thing you do is, once again, as we said, the preset or initials, right? And see what the initial the breakthrough curve, non-isothermal, just let me know. And I will track back to say what we did and what we assumed here.
Sir, before plotting the breakthrough curve, we have to initialize,
Yeah, that was the previous slide. So you must initialize.
Initialize are done.
Yeah, and you must initialize, and then you say
Here also,
initialization. So you must initialize and then run the initialization back again before you run the dynamic, the non-isothermal model. Here, I would like to also discuss that what we assumed here. Let's see, we are on the same page. If you have any difficulty in running it, just let us know and one of us will come and help you on that. Okay. Hoping everybody could run it. Let's see what are the things that which we specified and why did we specify. There are a couple of other things that I will also like to show you here, that these specifications means a lot. What it means is that based on this specification, behind the scene, Aspen will populate the variables for which you must provide the value or it will take some default value. So for example, let's see, we'll go one by one. So energy balance, we are making non-isothermal with solid conduction. Another was gas and solid conduction, and I simply said, yeah, let's only keep it solid conduction. Can anybody guess why I just suggested that? Is very low. Yeah, is very low. So it does not really matter. So it will make no difference. It will just unnecessarily increase the computational expense, and we want to avoid that part, right? Now, we did not want to do no conduction because the solids actually touch each other, so they do conduct. So that is why it is important for us to take care of that. We basically say consider heat of absorbed phase none. This could be a difficult one because many cases, that is why you see they always ask for the usual procedures about these heat capacities and all of that, because there is no really good or correct way of estimating any of these things. Mostly it makes sense to have these as a function of heat of adsorption, just overall do a overall thing there. I wanted to ensure that we are also on the same page, that many of these Aspen will allow you to provide the user-based option. So you can do an user procedure or you can provide a user submodel. So if you provide the user procedure, like for example heat of adsorption, by default we have it as constant. That is the simplest one that you can think about. But you can do it as a user procedure. You see that when it is doing the user procedure, I selected it. So now if you come into procedure, it came with row user underscore G underscore DH. So this is the user procedure. So where is that user procedure there? Like if you go under here, you have to write the code, but what it actually have here is that you have to go to the libraries, add sim, and then this is a procedure, right? So this is under procedures, so it will show you under that. So you will see there are a bunch of user things. So one of them would be this guy. Yeah, is this the one? No, this is the one. Yeah, so this is the one actually. So now if you double click it, you will see that what is the form of it. So if you want to have an user model for your thing, these are really advanced features. If you want to use any of these, then this is how you should be actually declaring. So it gives you a kind of a general format, and you can write your equation as part of these actually. It basically saying, yeah, I give you this, and you can actually write all of this code, and it basically say what are the inputs and how it has to be done, and then how all of these calculations are being done there. This is the same thing for many other user procedures. So basically meaning is, if you want to have, like you see for many of these things, so the moment you selected user, it automatically dropped this guy, right? And if I go back here and we basically say, nope, I don't want it, then it is updating it, it will delete that one. But otherwise it is looking for the subroutine, so it will not take the constant value, it will go to the subroutine and look into that. The same way the heat transfer coefficient, if you say, well, I want to do an user procedure, then it will go there, and it should not be confusing, because when I go to the user procedure, it already said what it is. And once again, this is row user underscore GHTC, one of them would be here. So this is the guy. So I just wanted to also give you an idea about that, when if you want to use it for research or advanced application, what are the bells and whistles you have that you can really play with. So if you have a complicated isotherm model, if you have a complicated heat transfer coefficient model and whatever, then you can actually use that. There is also another thing I wanted to tell, that under each one of them, you will be noticing that, so I'll remove this, I'll say constant as we had before. Another thing I wanted to say is there is called a user submodel. This user submodel is you bring it in, and you can actually, this is one way of telling Aspen to do it. There is also another way that whatever is the heat transfer coefficient or anything that you have, you can declare that as a free variable and write your equation within the flow sheet constraint. And I will show you how to write one such equation. These are all really advanced features, because this actually gives you the strength of doing pretty much anything and everything. Only thing that you cannot modify is the underlying equations themselves. But any parameters, any kinetic model, any isotherm model, you can always write your code and put it as part of this. So you do not have to use the constant values or the default ones or anything for yourself. So that is one way of doing it. So what I'm saying here is that even if you put it as a, when I put it as a constant, notice that for each one of them, when you have this, and then it has got, okay, I will discuss that probably in a second from now. But let's see, anybody has any questions so far? Okay, so one of the things I wanted to tell you here is that now that you run the code and you plotted the breakthrough, there are many other variables that are there which we really should look into, and we have not looked into. It is generating results for many things, right? So for looking into these results, you need to click on this guy, the block, click form and say all variables. It will give you the value for all the variables. So you will see how many variables are there. This is a massively long list, actually, just keeps going actually. So all the things that is actually, it is calculating, and everything that you have specified, everything is here, right? Whatever you specified, like this one is, say this is fixed, and whatever values you have, so all these variables, it is actually calculating. So if you are interested in any of these variables, then this is the place for which to where you have to really come to. So do look up for these additional variables that you have over here. Okay. Sorry. By opening, what you can do? Sorry. Oh, okay. So this one you are getting from here, but remember these variables, it is populating all variables that they are. So free, fixed, initial, rate initial, all the things. So how did it populate all of these? Like for example, you said this is dimension 1D, just I will show you here. Component list 1D, dimension 1D, internal heat exchanger none. So I'll just show you 3 of these specifications from where it got it. So if you come here and if you notice here, spatial dimension, this was provided as 1D, internal heat exchanger, we provided it as none, and then component list, it is getting it from here, is the default. Okay. So everything that you specified, it basically populating it based on that one. The other thing to notice about here is that under the configured option, we said number of nodes equal to 20, right? That's what we said, 20. So that because we said 20, everything it is discretizing between 1 to 20. So if you notice these results, everything goes from 1 to 20. You see all the things, these axial distance, the concentration, profile, compressibility, blah, 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 CV value, CP value, delta H node, everything. You see that whatever you populated, it automatically actually did all of those numbers from here. See? Right? So that's where it actually gets all the numbers from. So this, for everything that it did, all information here, and you can just like what you did for plotting, drag and drop everything from here. Okay. Unless there is any question so far. Next thing, I wanted to spend some time in doing the visualization and analysis. So these plots that you generated, you may not be happy with how Aspen formatted it. Then one thing I'm actually asking you to say, compare the results between isothermal and non-isothermal. So you want both the breakthrough curve together. And in the same plot, you might like to do something else. So you may not like these plots or the things like that. So you like to take it from Aspen to some other software for doing some analysis and plotting and all of that. For doing that, what you really need to do is that right click on your breakthrough curve, and click show as history. The moment you do that, it will create a table. Just top click at the top, and it will select the entire thing here. I will just go to the presentation mode quickly again so that you see what is happening. So you see, it will create a table for you, and then once you click this top one, it will by default it will select all the columns. Then you can simply say copy, and then you go to Excel and you say paste. Then whole thing will be gone there. Notice also that when I went to table form, it brings it as show table as plot. If I click it, it will bring it back in the form of a table, in the form of a plot. So you can toggle between table and the plot, and all those things go one as you really want to do that. Okay. So you can actually compare the results from your isothermal model and the non-isothermal model that which we develop now, if you wish, right? But we'll probably keep it as an exercise for later. I'll just probably move on, but these are the some of the thing that you really need to look into, that how does the result differ. So you have to copy the one from your isothermal model to Excel, the non-isothermal model also to Excel, plot it there, or if you're comfortable with MATLAB, this copy and paste will work anywhere. Put it in Excel or MATLAB anywhere, and it will actually just populate from that perspective. And then analyze how the temperatures and everything look like. Okay. The next thing that I wanted to do is something interesting, which is a spatial profile. So remember, this is a partial differential system. So what we really want to see is we would like to visualize the concentration, but if I'm looking into the concentration at any point of time, if I'm looking into, say, concentration of CO2, and this is with respect to space, so 0 to whatever, like L. And what we notice there is the concentration of CO2, I don't know, maybe at some point of time it is like this. Another point of time it will be like this. Another point of time it will be like this. It will be like that. The same way, if I'm looking into the loading with respect to space, and this is with time 1, this is time 2, like time 3, whatever. And then the same way for the loading, I would be expecting that initially you will have a very high loading like this in the beginning, and then this guy will probably not change much, but the other places will be coming to this loading. This will probably remain the same, and these other places the loading will go up. So the way you can see the spatial variable changing with time is by plotting these spatial variables. So for doing that, again, go to those plotting window that which you are aware of, but now you need to select their profile plot. You see there are a bunch of options there. Previously you already did the plot. Now you select profile plot. Right? You know how to do that new form. So, and then name it and plot it. Then what you do, you go to the bed and select all variables, then scroll down to this variable layer 1 dot y1 CO2. We would like to plot, I'm sorry, there is a typo. I wanted to mean W1 CO2 here. This should be, instead of N2, it will be CO2. But what we want to see is the layer 1 CO2 and layer 1 loading. So this is the gas composition loading and the temperature. So drag and drop those to your plot. Once you drag and drop to their plot, you need to change the name of them. So by default, it will be showing something like this. So you say TG or CO2 loading or CO2 gas or something like that. If it is not working for anybody, just let me know. There are a couple of steps actually. I want to go one by one and say what it is actually doing. Yes.
Sir, I opened this one. So how to get the TV and
so go to the model. So keep this open on the sides, but so right click and all variables, and then go to that one, like layer 1 Y1 CO2. So because this is Y1, so that you can imagine that will be actually very bottom at the list. The layer 1 Y1 CO2 and W's, the Y and W, these are actually pretty down below at the list actually when you go to the layer 1 variables. No, these will all go to the y-axis. Because what we want x-axis, because it's a profile plot, it already will populate the space for you. So Aspen by default, because you selected profile plot, it already reserved the x-axis for space. Previous case when you did the plot, it reserved the x-axis for time. Now it reserved the x-axis for space. This is an interesting plot. You will see as you keep running, this plot will keep jumping up and back.
All three things, y, w, and temperature, EG, all go to the y-axis.
All go to the y-axis. Y, W, and temperature all should go to the y-axis. So right click layer 1 like the bed and then go all the way down in the all variables table to find out these variables. Once you have done that, the first step is to click the profile variables. Once you have populated this, then the right click on the plot and click profile variables. Anybody running into issues? Oh, okay. Right click profile variables. The moment you do this, this box, this window will actually open up. You will see that by default it will write it as profile, profile 1, profile 2. So what I said is that we need to change it to some meaningful name. Like we say TG, CO2 loading, CO2 gas, or whatever. It's up to you. Yeah, just do up to this bullet and then we'll go to the next one. Next one is something I wanted to tell you guys, but do up to this one if you can. Doing good? Yeah, just double click on, yeah, now you can type it. Yeah, good. You drag already and changed everything. Oh, okay. Oh, yeah. You're getting pro actually. Right, okay, so we...
Temperature is coming.
Right, we'll say that actually. So actually if you have done up to this, then I will say keep moving forward to the next steps. If you have done up to this, then you need to go to the next one, and I will see what it is, but I'm just basically saying everybody done with the third step, or this bullet actually. Seems like you are good here. You're having issues. Let me know you are good. Oh, okay. Good. Seems like we're going good.
Yeah, they're doing
Yeah. Right. You guys are good here or need any help? Okay. Okay. So just raise your hand and.
Sir, where is the W? Okay, this is the first.
Yeah, so just drop any. I just said W1, but you can do just drop any basically. W2, W3, W4, anything. Because what we are going to do here, if you have done up to this, which I feel most of you have done it, the next one is that under the profile builder over here, like what you really need to do in the variables tag, then you change these by starred, right? This is by layer number by star. If you do not change the layer number by star, it's okay because we have just one layer. But if you have a bed with multiple layers, like 2 layers, 3 layers, 4 layers, then you basically say, I want the whole bed. So that's why I just said put it by star. But we just have one layer here. And then you just put a star. That star basically tells you that I want for all the spaces, because if you do not put the star, you just get a point. That plot will not show up actually, because you are just plotting only one point over here, but putting the star meaning that you are putting it for all of them. So this is the way to tell Aspen to say I want all the array, the entire array, by putting a star there. Okay? You should be able to click and put a star here as I have shown over here. So let's ensure everybody's thing actually looks like this. You have to just click one of them and change it, then click this, then change this, then click this, and then change this actually. So do one by one, all three do one by one actually. Once you click it, it will give you the corresponding profile variable, then you put the star. The CO2 loading, the same way you click it, it will show you here, and then you put a star and like that. Sorry? It will be star, yeah. So that's why instead I just said one, but you could have dragged like 2 or 3 or anything. Only that one I drag because of the structure. There is no meaning for dragging one, but because we are going to replace that one with the star anyway. The next step is that, and this is actually kind of, I am almost forcing it to do something that you may not like, right? And basically say how to recover from it. The first thing is that the temperature and the mole fraction and the loading, they have got a very different scale. And plotting them on the same figure will not show up. The only thing you will see is the temperature. Mole fraction and the loading will not show up, right? So what you really need to do for doing that, right click on the plot and then select properties. Right click on the plot, select properties, and then select axis map, and then click one for each, and then click apply or OK. So then you will see this axis got split actually. Each variable can be plotted under one axis. So if you this is one really good features I have seen in Aspen. MATLAB, if you want to do these things, it's a pain actually to create this. But Aspen can create you like 10 y-axis, no problem. You just say this, it will create 10 parallel axes with their own scales and everything. So this is very good actually. Other thing I wanted to say that once you are done with all of this and you try to find out where my figures went, because once you close the figure, you basically keep looking, where is my figure? Everything will show up under the flow sheet, right? I will also say that as you are right-clicking and then getting the properties, see many other options that you have under the properties, where you can change the default color and the markers and the styles and lot of other options that it provides you for figure. So do explore when you have some time in the future. Okay, any questions or anybody is stuck here for this step? Okay, so moving on. The next thing I wanted to do is that I told before that, remember Aspen AdSim is built on Aspen Custom Modeler. So I can exploit everything that I did in Aspen Custom Modeler in AdSim. I can bring in a natural gas combined cycle plant model that I built in Aspen Custom Modeler, connect it with respect to here. I can bring in a CO2 compression model, I do it here. I can actually take the variable that I'm doing from here and do it for all kind of purposes. So we need to know how to access the variables and use something with this. So I will spend actually good bit of a time because there are couple of understandings that is important over here. So first thing is that I want to take all of these and I basically want to cap and understand what is the integral capture rate. So if you look into the CO2, so when we have the breakthrough over here, say, I do not recall what it is, but say this is the 500 second time and this is how it is. So actually the amount of CO2 that is slipping through the system is this. Everything else that is coming in, it actually captured. So I would like to know what is the integral CO2 capture over the entire period of time, right? So if I'm actually doing a CO2 capture at each instant of time, I will say what is the thing that how much I have captured over the entire amount of time. At every time I'm actually capturing so much of rate. This is the CO2 capture rate and I'm just actually doing it. So question is, how do you can actually capture that part? I was just talking to Professor Sridhar that I actually there is a syntax for integral. I had to just look into for a couple more minutes to find out. But this integral call is not working. So I actually converted it to a derivative. So what you can do here is that both ways it will work. So it is y is equal to this, but I can actually convert it to a derivative and I say this is this guy, dy dt. So this is what I wanted to do. So then when I actually solve it, this basically tells me that what is the final value, because it will keep adding that value, but at every point of time I'm actually calculating it. So that is the whole idea that what we are doing. But the point here is that you can do any calculation here. So what you should do, just as we learned in Aspen Custom Modeler, first you must declare it as a variable type. These are new variable that I created. So I am declaring this. Where I should do this? This is under the flow sheet and flow sheet. So during ACM class, I already mentioned to you guys. So please do click flow sheet and then flow sheet. The moment you open up, it will open up a blank slate for you. There, first thing I do is I declare it. So I just say CO2 in as flow underscore mole, meaning this is a rough calculation, so you can do any calculation you like. And the CO2 out as a flow mole, because this is the molar flow rate. Remember in the ACM class we said the variable type. So declared it this, and I say int, actually this is not the latest PowerPoint. Is the one that we saved here is sent here, or can you check out? This is not the latest one. There is another line of code over here actually, and this thing is shifted down, and please, because that part is a little complicated. I wanted to show everybody that one. Sorry? Oh, okay. Oh, you see. Okay, so it's okay. So they are seeing that one. So it's probably not the displayed here actually. Okay, it's there. Okay. So I think it's the one that is I'm displaying here doesn't have it. Okay. But in the meantime, maybe we can just proceed.
You continue.
Yeah. Yeah. So basically, first we are declaring it as a time derivative. So once again, remember how we declare a time derivative. We just simply have a $sign. So if you have the PPT in front of you, so just use it from there. So it should be a $sign, and then you write the term on the right hand side. Both variables CO2 in and out, I am declaring them as a time derivative. Again, you can declare any variables here. I am showing it as a one time derivative, two time derivative, and two algebraic variables. So once this is open, I wanted to show you here how to access the variable that is in the flow sheet, which is coming from AdSim, and use it for in the flow sheet constant for your calculation. So every variable that is there is accessible to you for doing anything that you want to do it, because it's again SEM, so you can just use it for anything. Okay, so that's the first thing you do. So if you have the PowerPoint in front of you, so you can just code it for now a little blindly, and then I'll go over, spend some time discussing that what it has, what it is there. Do you guys have the PowerPoint? The new PowerPoint? Yes, go about there. Yeah, this one, all of this code. Yeah. So it's the flow sheet. So if you go in the flow sheet, and then this is the guy, this one.
Oh, flow sheet.
Okay. Yeah, because you are already in the dynamic mode, it is actually giving you a caution that do you want to change it. So you have to, yeah, I think, okay, thank you so much. If you have a simulation running and you are under dynamic and it has already gone to like whatever 400 second and all of that, when you try to click the flow sheet, it will warn you, basically saying, do you want to bring it, or do you want me to come and bring in a non-editable version of this one. What I will say is that what you really need to do here, like for example, I have not run it over here yet, but the idea here is that when you come to the flow sheet, so this is the place I'm actually talking about. For me, because I have not run it, so that is why it is actually giving me the thing. But you see that, for example, if I've run it, okay, and I can stop it at any point of time, then I will get this message. It's basically saying, this will be changing the structure of the current model. Do you want to stop the run, or do you wish to continue? All of those things. What I will say here, if this is the case, simply say cancel. And then the thing what you really want to do here is that simply come to initialize. You say yes, and then because we'll have to do bunch of things here. So that's why it will take you a little bit of a time here, and then simply do the initialization. Once it is done there, it will not complain to you. So come to flow sheet and come to flow sheet. So it will open up for you. Okay. So initialize it, run the initialization problem, and then make the changes as needed. Okay, so let's see what are the things we are doing. I think at this point you can just first blindly copy it here if you like, but see what we are actually trying to do if we like to understand it. So first is, this is the way to access a variable. So this is the feed. So this is the feed, this is the block, and then this has got a variable called f. So feed dot f, that is how I access it. Then this variable is called, it has also got another variable called process out y CO2. So that is how I access it. So see, for example, I'll show you here. If I go here, maybe I'll close this, guys. So if you come in your feed and you see form all variables, so you see this is the variable I'm accessing, feed.f. In the same way, I'm getting this variable feed underscore process out y CO2. So you exactly copy these variable. So the way to access is that whatever is the block name dot this, and if there are additional dots needed, Aspen will tell you those dots. That is how it will actually display it over here, but this is how you access it. Then I'm doing that same thing for the feed and the output. And then we are actually doing all this calculation here. For the average loading, there are different ways to do it, but I wanted to show you a sigma function that sum up thing over an array. how do you sum up or do anything over an array? This is how it shows up. So this can be done for space, any space also, like you say, I'm doing it over this, I can use this for over a time array or spatial array or anything. Anything is an array, you can do it. So basically I'm saying sigma, open parenthesis, for each, there is no gap. Remember this one. There is no gap between for and each. For each I in 1, 2, bed dot layer 1 dot nodes. What does it mean? So that basically means is 1 to 20. So if you see bed 1 dot layer 1 nodes is actually 20. So I will go here, and if you see the all variables table over here, so this is the guy. So layer 1 dot nodes. So when I use that, it will return me a value of 20. So I want to sum up between 1 to 20. So that is what it is actually doing. Then I'm saying, what do you want to sum up? The variable that I want to sum up is the bed dot layer 1 dot wi, because I want to do it for all of those nodes there. And then this is within this CO2. So remember, this is the same way that which we are calling these guys here, but there is a difference here. The W, this is indexed because it's crucial for the code to run, which I will wait for everybody to type it in, please. Yeah, that sigma function, be careful about this one. With this is a integral percentage capture. This is a variable I just named. Yeah, I just named. You just declared it anything. I just say integral percentage capture as a variable, but you just can do anything you like. Yeah. Okay. Carry on. This guy can give you trouble. You will not understand that you made a typo till the next step. So we'll say what step will tell you there is something wrong.
How will it integrate with respect to time?
Sorry?
How will it integrate with respect to time?
So this is basically why that we are trying to do. So we'll do the dy dt, return me the last value actually. Yeah, but you can do the integral also.
It will automatically
Yeah, because I'm doing the derivative, so it's an extra time derivative. And because it is tracking the y, and that is why I'll start with the initial value. You will see that from where it will start. And then it will integrate over the period of time. So it will say how much flow has gone through the system, how much CO2 over the entire time has gone through the system. Yeah. You can do it. There is also an integral call actually. I'm just could not quickly find it. I think it should be integral open parenthesis argument comma time. I have to ask one of my students actually to exactly that call is. Yeah, it was returning me error, so I avoided that. But so I used the derivatives there. Okay, so yeah, be careful about the number of parentheses, and this one is this square rectangular brackets actually. Remember this one. So it will. This is an array, so you have to use this rectangular bracket. So be careful about declaring array and these arguments. These are different actually. So to understand if you did not, whether you made any typo or anything, right click over here and then click compile. That will tell you that if you made any syntax error, any typo or anything. Yeah, right click over here and then click compile. No, this is SEM. Remember that day I was just saying that it is actually Aspen Custom Modeler. So this coding is actually Aspen Custom Modeler. Yeah, I actually say this, actually in my last slide I talk about this, but there is an Aspen Custom Modeler help manual. If you, because you have the license, you can actually download that one. Yeah. Most syntaxes you will be fine there, but there are some tricky syntaxes you will be a little, maybe a little difficult. But this is what we are showing it. The one they would not show that within AdSim environment, how these things can be brought in. Those things are not there. So that's what I wanted to show it here, that it's AdSim with SEM features, what you can do actually. And when you write, yeah, I will hold on for that one, that what else you can do over here. Okay, so let's see if compilation is successful, then you are good. If your compilation is successful, you will see a green over here, like what is the status? It will show you green with an arrow pointing downward. So click on that arrow to find out that what it means actually. So do check it out, and that will tell you something very interesting. You did that?
Done.
Is everybody with me or? Okay. If you compile it, so this will do an compilations. What you will find that under the status sign over here, it is not green. It will be an arrow with showing downwards, and you bring your cursor to there and tell me what you find. Sorry? Oh, you already specified as initial. Oh, you went forward actually. If you follow my slides, you have probably gone forward, but I wanted to walk through that one because this would not be obvious that why it was doing this. When you try to do yours, you will run into this trouble. So the point here is, this was, if you do not do anything, by default, Aspen will treat these two as free. If you do have these two free variables as free variables, then it is under by 2, because it is basically saying I just cannot calculate it. You need to tell me initial value for these ones. So that's specification, lower specification. So see, this is the difference in the sign. It is a green with an arrow pointing down versus it is a red or like only an red arrow pointing down or red arrow pointing up. This is basically telling you that it is square, but there are two specifications you need to look into. So what you can do is that you say, well, this is time derivative. So what you do there is that you go here and then change them to initial. So go there, and if you're seeing that arrow, you need to change them from free to initial, because these are the time derivative. Now one question immediately comes there is that these new variables that I created, where do they show up? They will all show up under these local variables over here. Everything under the local variables. So click the local variables tab and ensure that you can see this. All the variables, and it will create you all of those things, right? Now, I said that provide the initial values for CO2 in as 3e minus 7 and CO2 out as 0, and I just need to provide these values for these time derivatives. So how do I get this value here? I basically, what I did here is that if you look into the f times z, so the initial value for that variable was really, I just took the f value and the z value and I multiplied it. If you notice here, at least the simulation that I have, the flow rate is 3 minus 6 or whatever, and then no, probably 6e minus or something, and then we multiplied by the mole fraction. So this is the number I was getting. So that is how I got that. So just to ensure we are on the same page, these initial values of whatever is the CO2 in, I simply went here and basically looked into this feed. I have already the all variables table. So this is f times these z that I actually multiplied that, and that is kind of roughly gave me that number, right? So 2 and this is 0.15, so it is kind of a 0.3 E6, so 3 minus 7. An outlet in the beginning, there should not be any CO2 going out from the system. So that is why we have that as that number there, like all of those. And you just need to provide that with only for those two variables, right? Now, interestingly, see here, so this is the local variables table, right? I have that, and you can, this just becomes a different numbers because we are looking into something else, but you can, I can just type it in like what I said, 3e minus 7, this is, I have it as 0. Keep an eye onto this variable here. It is drawing it from before, right? If I just say initialize, it went to 100 because this is the value 100%. So remember, and during the initialization run, Aspen will solve all the algebraic variables. It is only the time derivative for which it is looking for a value. So it will take the values for the time derivative, initial or rate initial, and then given that value, by substituting those values, it will calculate for all algebraic variables. So that is why I can type it any number. Remember, I did not ask you to specify any value for this capture, but I only asked you to specify this value. Once again, I am showing you. I just put any value here. Remember, for algebraic variables, I said this is just a initial guess, right? So if I do this and take it, it will overwrite it, 100, okay? So far so good, everybody is on the, which one? Yeah, this one, okay. Okay, so now what you really need to do here is, once again, you need to do that thing. Go to initialization run, initialization button, initialization, and then run this. But I just wanted to, before you go here, I also wanted you, before you started doing this, there are two things which we like to observe. And again, you can observe it one by one or you can observe it together. But this profile is first thing I will really like you to observe. So what I will say here is that the plot that which we generated over here, I will suggest you open it and keep that open and run this breakthrough. So go back to initialization, initial, open this profile, and then run the simulation and keep this profile open. You will see that how that spatial profile keeps shifting with respect to time, right? So this is the variable, this is the profile. I just said initialization, okay, and then if I run it dynamic, notice that it will be actually with respect to space. So this will be an interesting profile for you to look into to see how the overall profile keeps changing with respect to time, and you can analyze it, why it is behaving this way. And one problem here though, Aspen automatically keep adjusting the axis ranges, so sometimes it might look confusing to you actually. You think like, well, why it is changing, but it is basically because it is changing the axis range over here, right? So that is one of the things. And see, you finally after done, it did that. So again, what will be suggested is that you come here and you can plot the axis range to a range that you wanted, right? If you say 265 to 325, so it just click onto this and it will give you the axis range. So if I want to see it between 265 and I'll say apply, this is how it is actually. And okay, and then this guy is also, you can say by default it went to -1E5 to 1E-5 and all of those things. So this kind of gives you an idea of how you can actually visualize, how you can code all of these things and have a script to do some additional calculations, okay? Then I would also like to rerun that same code, go back to initial, rerun the code with now opening the local variables table. Now reinitialize, run initialization, then open up the local variables table and keep an eye on the percentage capture. That variable you will see as you are running, it will be actually keep updating it, that one. And notice that the integral percentage capture keeps dropping with time. And why is that? Everybody able to run? And look at your local variables table that you just created with these variables, and as you run your code, keep an eye on the integral percentage capture and notice that this integral percentage capture is actually keeps dropping with time. So why does the integral percentage capture drop with time? Is slipping from the system, right? So this is the whole thing. So if I'm actually considering here, this is 100% capture almost. I'm coming up to here almost 100% capture, but because this is getting time average, so at this point it is not capturing anything, almost, like when it broken through at the top. So that is why it is actually showing you that overall capture percentage, integral capture percentage is actually going down. Okay. With that, let me see if anybody has any question here. There are other things that is there, but we kind of avoided doing that because it will require quite a bit of time to do that for the regeneration and cycle. But I will show you a couple of things here. So, but as of now, anybody has any questions or stuck up anywhere or any help? Results are not. Say that again. Results
Results are not correct.
Okay, so finally, when it comes to the time when it actually breaks through, then you will not see any special change in the temperature, because really once it breaks through, nothing is changing. So the CO2 concentration, nitrogen concentration, temperature, everything will be a horizontal line, because once the bed is not capturing anymore. So for example, when you are looking into here, if it goes to the top values here, so if it goes here and goes like this, and it goes here and goes like this, whatever, beyond here really nothing is nothing is happening. So your concentration profile during that time, when you look into through the bed, it will be a horizontal line. So at the end you will see horizontal lines. So in the beginning you will see a lot of dynamics going on and all of that. Another thing that you might have noticed when you are looking into the spatial profile, in many cases, and this was something which I was thinking, really somebody will ask me, in the sense that this sometimes do not look reasonable. And you see the CO2 concentration, and this is with respect to space. Many times you might have actually seen that the CO2 concentration is almost like, looks like a very roughly changing, right? It might be looking like this and look like this and go like that. And you will see that go and put like a line at some point of time, or the nitrogen concentration you might actually see at some point of time going up to like this and go like this. This is basically, if you see this type of a profile, that is telling you that you need to increase your number of discretization. It's not smooth yet. Ideally, it should be smooth, and these are all because of numerical issues that what we find out. Okay. Any other query here? If not, I have really just two quick things that I would like to mention, and then after that, I will say that really want to discuss this. For syntax and other information, this model language quick reference is something, when you go from here, like you are on your own, when you just come here, I will say adsorption contents is okay, but you can always go to the Aspen custom modeler contents, right? So as I said here, this is where everything is there. I think most cases it will serve your purpose, but other things that you can look into more details, right? So if I say model language quick reference, this gives you all the syntax and the structures that you need. Most essential structures you will be able to find under this quick reference guide actually. You will see like how this actually looks like, how you have to have a distribution, how you write any of these. It also gives you some code over here that how to write any of these things, how to write for loop for each, like the one that which I used. Yeah, you see that this is the one for each actually. That syntax there Then for writing the model, it also gives you a very nice structure about how you to do that. It gives you operators like conversion operator, logical operators, math operators, whatever they have as part of it. What are the different parameter types, port types, procedure, call, definitions, and all of those things, all the options. So do look into that. I think most of these will be available there. Other thing which is actually absolutely critical, and I will suggest that is where we are living here. I will have to see if we have any time tomorrow, because setting up desorption is actually time taking. But we'll show you some of the references and what goes into there and where is the problem. That we'll talk about that, and maybe I can actually record some and we can post it as a later PowerPoint slides. See program file, Aspen Tech, Aspen Adsorption, example files. Here you will have got actually a lot of examples that they have provided. Out of those examples, those ones which many of these has got only the adsorption, but many of them has got also the desorption and including the cyclic steady state. So wherever they have this thing for saying cyclic steady state, CSS, this basically stands for cyclic steady state. I just quickly want to go over it, but if anybody needs, probably we need, how do I go back? Oops. C and is this the user folder? Where do I get the access? Or it's all under, maybe I can put it under desktop if that would be okay. Or maybe under the documents. Yeah, maybe under the documents. Okay, yeah, that's where you have this here. So I'll just put it over here. Okay, hold on. And then if you come over here, you will see there are two files over here, right? I just wanted to quickly show you what is involved, and it takes actually a little bit of a time, and then you have to really, an hour, 2 hours is not sufficient because you have to understand this whole thing here. So, but once you become more familiar and play with adsorption part, then the desorption and cycle setup is the more important thing. Okay, so let it open and we'll show you this. So this is a system where you have the cycle setup. When you try to do the cycle setup, there are two things which you have to do it. One is that you have to have this tank thing, okay, and then there is another systems that which you have to kind of think about an interactions. So it's because there are actually essentially two beds. So you have to kind of actually dummy another bed for that one. Everything else you have already studied. So this bed is the bed which we considered, this one, this one, this one, this one, all of the things that which we have already considered. And of course, these valves are there. So remember, these are the valves that which we need for pressure equalization and the purging and all of those things. And if you use steam or anything, you have to connect your steam to with respect to this, and you can use one of the mixer blocks here for doing any of those stuff there. The main guy over here is called the cycle organizer. Okay, the cycle organizer, if you come here and if you double click onto cycle organizer, it actually shows you that what are the things in the cycle. It has a step 1. So it is basically saying this step 1 is the feed pressurization, and it is time driven. So for this case, it is 30 seconds. I can do it for any time, like 40 seconds, 1 minute, whatever. It can be event driven. So question is, how do you do the pressurization? You can basically say, I want to always pressurize for 30 seconds. Or you can say, if the pressure is higher than this, then or greater than equal to this number, then I'm happy. And that could be shown under the event driven, and it is saying value and the variables and what equation you want to do. Then it gives you step 2. Then it says, it kind of gives you an idea that feed plus product plus parts out. So time driven, again 40 seconds. Then step 3, it is saying pressure equalization out. Step 4, depressurization. Step 5, again the time control by step 2, again same and the same way. Once you do this, if you click on the cycle, it gives you the setting of the cycle. So it basically says how many cycles that you want to do. Remember, at the end of this box gives you a cyclic steady state mode. This was the thing which I was saying, that you must check this box there if you want to set it up for the cyclic steady state. And what it will do is, basically it is saying 20 cycles I will run. So it will run adsorption, desorption, adsorption, desorption, adsorption, desorption. How many maximum cycle? 20. By which, if you do not achieve cyclic steady state, it will tell you that it is failed to achieve cyclic steady state. That basically means is you need to increase the number of cycles there. Then it actually, for each of the steps, it has got control, manipulated interactions. So if you look into any of these cases, right, and you will say, okay, what are the manipulated variables that I have? This is basically saying, let's say, for example, for step 1, I want to see what it is exactly doing. It is basically saying at step 1, feed pressure dot spec, that value is at 2 bar. It is saying keep it fixed, don't do anything with it. There are a bunch of variables that it is actually fixing at that step. So this is the way that we talked about the cycle, that the valves needs to be opened up. You need to ensure that this side of the valve is open, other side valve is the closed. So this is where you actually specify each of the steps here, and you can say, okay, I do not want to go to a jump to a value. When you provide a fixed value, it will directly do a step jump to that value. But you say if there is a convergence failure, you can specify these under a ramp. So you can say linear ramp or a S ramp. So that case, the linear ramp is like this. So if I'm here, it will do, this is linear ramp. If it is a S ramp, it will be like this. So S ramp is easier. So this is a S ramp, and this is a linear ramp. So if you say ramp it, then it will immediately say what is the target and over what time you would like me to ramp it. So if I click now linear, you will see that these boxes will open up. You see, these new boxes opened up, and by default it say, okay, target is 2, yes, and the time is 30 seconds. So that means that whatever value it has from here to here, it will go there within 30 seconds. This can avoid convergence failure for many cases. So you can set it up like this way, the same way you have it. So step 2, these are the things that are changing. So all the variables that are changing at step 2 are actually listed here. Step 3, these are the things. Step 4, step 5, step 6. So everything you can actually specify under the variables steps over here. So these are the manipulated variables. If there is any interactions, you say this, what are the interaction unit and what are the bits that you have over here. And then of course you can have any other thing that is not listed there that can be executed at part of this. And if you want more step, just simply add or insert steps. So when you have this cycle organizer, that actually you can, based on your simulation, you basically say, I do not need step 3 and 4, it will by default, it will start with only one step. And you can just keep adding more steps as you need it, and basically say this valve open, this valve close, and all of that. That is why it becomes tricky to do that. You will have to take some time, draw a cycle picture in front of you for your system, and then you have to basically run these things accordingly. if you really want to see what it is doing and what is under the code that is happening here, the actually, no. So what you have to actually do here is that this is under here, and you will, by default, they have it over here. Sorry, I think you have it. Let me see this. Yeah. So, okay, before I go from here, I just want to say that this also lists you like the all variables that is under here. Whether the cycle organizer runs or doesn't run, that depends upon what you have set as a task. So as I will probably, if I have time, any time, yeah, we'll probably have some time, I will go back to that Aspen custom modeler thing. That actually I could not cover that day, but everything is covered under there really, that how to set up the task, how to do it. This is actually set up under task type. So basically, if you look into the task, so it's a global task, probably libraries, and where it is, that same task. No, is it the system library? Yeah, so these are all the different tasks that which you can actually run as part of this whole system. So everything that you do here is actually goes under the task, right? So it is basically saying I'm looking for the task cycle 1, and then once the cycle 1 starts, then I can actually would be able to run this overall code over here, that which you have this. You can have these tasks listed. If you, right now we do not have anything here, but you could have this task listed as part of your own work here. Okay, so these are generally the thing. But this code is that if you look into, yeah, you can see the active model. You have to yeah, so this actually is a cycle organizer 1. That is what is the active model that it is actually calling. It gives you the reference when it was last updated and all of that. And then all the variables are as part of here. Let me show you this one. Properties. No, you just actually. For other thing is that if you really want to see any of this code here, it also shows you the path where it has this whole thing actually. This is under the library, under the call the cycle organizer, and that is what you do there. You can just simply copy and paste this cycle organizer to any systems, and then you can modify it. That's how this whole thing has to be worked out. And these are actually the tasks. So this is like doing a ramping task and all of that thing. But again, we have to really see this, that it may be useful for you to, if anybody will be interested, we may be able to record these. But everything is under the user files, and these setups can actually be copied. I will just actually stop here for this and see if anybody has any questions. Otherwise, we'll go over any other leftover points there, and then I just wanted to see that if I can go to my day 2 notes for Aspen Custom Modeler end, because these are all built on Aspen Custom Modeler. So we really need to understand that section to see really what is going on here. No, it should be in your program files. These are in your, when you go home and you see your, like your home organizations, you see that program files, and it should be there. It comes along with Aspen actually. Yeah. There are some really nice videos also. I'm just, only thing I do not know whether those are shareable or not, but otherwise we can just record some of those things. and you can actually utilize it. But you have to actually be careful when you do it, because you must know first the sequences by which you would like to go for. Okay, anybody has any question here for us? If not, I add all the notes here. So I just want to see this guy, yes. No. It's part of the tutorial, this guy. Okay, I wanted to go over some certain things here that what I left over, and I think these are actually very important for us to understand what is going on anywhere. One thing which we did not discuss here yet. So remember that we talked about the snapshot management. So that is important. If you actually run a simulations, always do a good snapshot management. So you can always come to the camera icon and take the snapshot. We discussed that on that day, but let's say I want to take a snapshot at 500. I can save it, and the next time I can load the snapshot, it will directly take me to that 500th point. So that is important for any of us to really look into there. The other thing is that, yeah, this taping, simulations, and other things are important. Okay, we did not spend much time, and I promise that we will. So let's look into this section a little bit. So the solver option, I'm directly presenting from here. Hope you can see these things. Or you can just open it up. So open up, please, the solver option. So click this green thing over here. This is the solver option. If you open the solver option, the first option that I would like you to open is the integrator option. By default, it will select implicit Euler. When you have implicit Euler selected, see the maximum order box is grayed out because the order of implicit Euler cannot change. Then you can do Runge-Kutta 4. Again, this is grayed out because it is the fourth order, so nothing can be changed. But if you do the gears method, you will see that it becomes, just select the gears method and you see the order, that box is not anymore grayed out. So you can type whatever number you would like to do. Here, there are a bunch of tolerances. That is what is actually talking about is absolute integration, relative integration, absolute tier, and the relative tier. So absolute integration basically means is integration error in terms of absolute values. Relative is between whatever is the value that you have in the past versus right now. So those are anything with respect to a ratio is known as the relative error, and absolute is that whatever error that you have in terms of overall integration. The tier, I do not want to go into that further, but the tier integration, if there is a tier variable, this is also a difference in Aspen versus MATLAB or Python. If it may create a tier variable that is actually solving for it. If you are familiar with Aspen Plus type of an environment, this will give you an idea, but this shows up under the solver messages that what those tier variables are, right? So just to ensure that we understand that. So for example, if you do have, say, a reactor and you have a, say, a distillation tower, it goes like this, right? And say this comes back, maybe it goes into a separator, maybe it goes to a separator, and you are saying unconverted reactant goes back like that, right? So if you have this kind of a cycle there, it can actually tear the stream. So tearing the stream basically meaning is that the problem that you have with this type of a simulation, which is done routinely in Aspen Plus, that same feature is there within also Aspen Custom Modeler. The issue with this type of thing is that it's a chicken and egg problem. You cannot solve this unless you know this, and you do not know this unless you solve this, right? So basically, how do you solve this? You actually tear it. You tear it. You basically say, I make a guess here, and I would like this to be exactly same as this one. So you say this is y and this is x. So you want y minus x equal to 0. This is the equation you solve. And then this y, this is actually is an array. So both of them are an array, because this has got the compositions like yi, pressure, flow rate, temperature, all of these things it will compare and basically say, can I solve it? So for our case, when I do not have any recycle or anything, this tier, even though that option is there, it does not matter for us. But whenever you come up with a complicated model, it will actually, the solver will analyze it and say, doesn't tier really help us? Most cases, if you do not have this thing, you don't have to worry about it. Okay? The other thing is that what you will see here, we discussed about this, when your adsorption isotherm do not, or your adsorption model do not solve, these are the options that you need to play with. I would say never use a fixed option. So as we discussed, use a variable option, and then we have the initial step size, maximum step size, and the minimum step size. So again, remember our discussion there, it will keep cutting steps till you reach the minimum step size. If you give too large of a window, it will keep cutting steps and it will take you forever before it says, well, sorry, I cannot solve it. So you have to be practical in terms of what you specify there. Okay. Within AdSim, because this is coming from Aspen, as I said before, for troubleshooting, like when there is a convergence failure, these are the two things I strongly recommend. Like you should at least see 5 and 5. If you do that and you say apply, as you are running your code, okay, it will keep generating those solver messages. Right now, it does not show you any solver message here. It's basically saying, I'm integrating from this to this. But if you really want to see any solver message there, and that if it fails to converge, those messages are the one that will tell you what is failing. So that is about that part. Other part is actually the nonlinear solver, which is important. By default, they have the mixed residual. There is a fully Newton based, there is a fast Newton, and there is a hybrid approach that they have over as part of here. It is saying convergence criteria is always based on residual, and another is on the variable. So the difference is that basically saying, if I'm actually solving this equation f of xk equal to 0, so this is that whatever value I am getting at this point, this is known as the residual. So by default, it is basically saying, is this residual close to 0? So with respect to the tolerance, I'm calculating it. But it can also take the variable tolerances as part of that. So basically saying, is the variable changing, xk plus 1 minus bunch of other options. There is a dogleg methods. Again, I'm not sure you have studied. There is something called the Powell's dogleg method. So if you're interested, just read these things. Wikipedia has got a lot of information. Powell's dogleg method, and that actually helps you to, if you have a degeneration, it helps you to recover from that situations there. Okay. there are a bunch of options over here. The default, I will say, work generally okay. What I would suggest you to do here is, if you run into the thing, is that max iterations. This is really, in some cases, it is actually too much. So what happens is that if you are doing 500 iterations and it does not want to converge, you really do not want to go for 500 iterations. 100 iterations is enough for most systems. If it doesn't converge, it's probably not likely to converge. It's something wrong. It's better utilize your time figuring it out rather than waiting, hoping that the solver will solve it at some point of time. So you will do that one. The creep is can help you in, if you are actually perturbing some parameter, like I talked about initialization, there, like I talked about the reaction kinetics. So the reaction kinetics, like for example, if I'm actually considering a reaction kinetic parameter, remember I talked about the initialization, that step-by-step initialization is important. And in this case, is you have the, one of the parameter is changing. So for example, if I have a reaction parameter, say A exponential minus E over RT, concentration of a alpha 1 and blah, blah, and assume that this value is 1 to the 10 to the 12 or whatever, right? You do, and if the moment you turn it on, this will fail. But what you can do is that you can consider a creep parameter, like something like that, and then you slowly crank it up, like you say 0, 0.1, 0.2, 0.3, something like that. So that creeping, and then there is an option here, they have the homotopy based approaches that you can actually utilize this. So these are homotopy approaches. So there are homotopy continuations. Again, in your numerical methods class, I'm hoping that you have studied that. So these are the options as part of that, that I will say that can actually help you to find it out. Here again, for the nonlinear solver, the highest variable steps and the residuals, you can turn on 5, 5 or 2, 2 or whatever. That gives you a lot of insight which variables it is failing to converge. Then finally, the linear solver, I will say there are two options. I do know there is also a latest option that it does not have here. But to be honest with you, there is not worldwide much progress in the linear solver. These are still the state-of-the-art linear solvers, and they do all the grunt work behind the scene. That is all done by the linear solver, but these are old solvers. These are ones based on the HSL packs that which we use for this MUMPS linear solver that I mentioned here. Those are some of the part of the HSL packs, but those, they sell those solvers in the market. It's Aspentech does not have some of the latest linear solvers. But these are still old, but still almost state of the art, I will say. But they do a lot of the works there. You do not see much thing that you can really do over here, but they do not expose it. These things are, when you use some other solvers, these solver settings are actually tricky with linear solvers. You have to really understand linear algebra. These are extremely complicated routines actually. So we'll not talk about that one. Some of you are actually asking me about some questions about what are the other tabs used for, like estimator and optimizer and all of that. When you run into here, that there is an option called estimation and optimization. Estimation is the tab you will be using for like isotherm parameter estimation or the kinetic model parameter estimation, the one that which I was actually showing here. So if you do it, it will be, you'll have to select as an estimation, and then what you have to do is you have to come under the analysis tools, and then you have to go for estimation, and here you have got bunch of things like a steady state data and whatever, and then for each one of them you can actually create that what variables you would like to estimate, and how, if you have experimental runs, then you can find it. You can just bring in the data for any of the variables that you have. So I can say these are my steady state experiments, or these are my measured variables that which I have as part of this, and I would like to bring it there. Estimated variables may be the isotherm parameter. If you are estimating the adsorption isotherm parameters, then estimated variables will be those. It will let you find it. So here find, and there, so remember this variable find tab is kind of a save you for under many circumstances. This is a wonderful option in Aspen that gives you lot of things, lot of information that you really like, and even when convergence failure happens, then sometimes this variable tab, actually variable find tab, will help you in finding out. So where you can find this variable tab, find tab, you can say tools, variable find. So here if I do it, I can say find in where. So it's a find in blocks, and I say which one, do you want it for the bed or the feed on the product? And I can simply say in the bed, okay, I can go down or whatever, but I can say feed bed, and I say okay, and it is asking what type of variable you are interested, free, fixed, you can uncheck and check those boxes. And if you say find, it will do, you see that it actually brings you a lot of information that does not shows up in the all variables table. So it will give you, you will see this, it will give you a description of all of these variables over here, right? It is saying free variable, what type of variable. Then once you are here, then you basically say select properties. So once you do the select properties, one of the big things that it basically gives you derivative and the units. If you ever get confused about what unit ACM is using or ADSIM is using, this is the place to do that, because many times we do get confused saying, oh, what unit, I write my own equations, I must be consistent with it. But this is the place that is actually tells you that. The other thing is when you have a convergence failure, so you many times the bad or the worst thing is you click run and the first step itself it will fail, and you have no clue what to do it. So remember the first step, if it fails, that basically meaning the guy who is likely causing the failure is the one which has got the highest initial derivative. So first you see that initially when AspenTech does, even under initial conditions, it will calculate the derivative. If you have a gigantic derivative, that basically means is that variable is going to make a very large move there. So how do I know which derivative has a trouble? That residual will not tell you that at that point of time, because it's at the initialization itself. So you need to come here and you basically click derivative and you say units, and you say okay, it is repopulate it. So you now see that it is giving me the derivative. Now I would like to arrange it with respect to derivative, so I just click it here. You see, now it brings me the highest derivatives that I have here. So you see, some of these derivatives are actually crazy actually. You see, there could have been, some numbers could have been there, but at this point, this is basically saying, well, I really do not need to worry about some of those because it solves. But this is the way to find it out. It also brings in the units here. So I know there are some questions about how do I know what unit it is using and all of this. See, it gives you the units that it is actually following for everywhere. Kilomole per meter cube is the concentration units, as you would expect. For pressure, it is or the compressibility, it is using bar. For these temperatures, it is using C and blah, 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 and all of those things. So then, and all of those part here. So this is one really nice place to look into and understand these ones, okay? But I did divert. What I wanted to say here is that if you are not a MATLAB fan, or you want to do everything in Aspen Custom Modeler, or You want to estimate those kinetic parameters, which requires the Aspen model. This is the place from where you actually do it, under the estimation. The other tab which is there is called the optimization. So say if I want to do an economic optimization or something, here it will let me do that optimization. It will say what is your objective function, what are your decision variables, and blah, 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 and what are the steady state constant, dynamic constant, initial values, control variables. So if you want to do like a minimize cost or something like that, you can actually write all of those things as part of here in the setup. And it also says, do you want to run a steady state optimization and dynamic optimization? So you can even run a dynamic optimization as part of it here. So those are some additional tabs that may be valuable for you guys. One thing we did not spend much time here is the run option. Okay, let me first change this to dynamic, then it will populate it. Be very careful about changing the units in your model here. This is probably the worst blunder that can happen here. Remember, as I told you, that Aspen internally do not track any units. So it wants you to be consistent. So it is basically what the option it is saying is that it is clearly telling you that select the time unit that correspond to the units used in your model. So when you write that equation dy dt, what is the unit of time here? Because you wrote all your right hand side based on that. If I did it in kilomole per hour, meter cube per hour, or kilomole per meter cube per second, or whatever, this will be a very big difference in the units there. So it basically says if you did use time unit as second, you select it as second. Remember, it will not even complain to me if I change it from second to minute. If it is in second and I change it to minute, it is happy with it. It does not have any understanding. It says, okay, this is the second, it is fine. Now, what you have here is that in this case, they have done some really careful things. If you write your code, you have to be careful because they have this global time scalar value that they played with, and that is why it will actually keep updating it. And I will show you what it is actually. But before that, there are three interesting things: is communication, display time, and time now is the current time. Communication and the display update, like this displays how quickly it is updating it, and this communication time is this simulation message. It does not mean that Aspen is solving every 1 second, if you say it is 1 second. But if you say communication time is 1 second, say I have kept the communication time as 1 second, and in the integrator option, I basically say minimum step size is 1. So even if I do it at 2, it will ignore that guy. Because you said my communication time is 1 second. So whichever is the lower, it will go for that one. Because it says the user is telling me you would like to see the communication every 1 second. But you kept it like this, so I just cannot do it. So that actually forces Aspen to do things. I don't see any issue here. Okay, so we discussed all of these options here. I think we discussed all of these options here. I think we discussed all of these options. Now, this is the task under which that cycle organizer actually works, and this is one of the reasons that I avoided this. Basically, how do you have these, and what are the things that you really want to do it here? So this template that actually appears, that kind of almost gives you an idea about how you write all of these. So for example, if you like to run a task at, so what is a task? So task is basically take the model, any variable that is fixed, you basically say change this fixed variable at this time. So if I have a valve opening, I'm basically saying close the valve. So valve.op, set it to 100%. Task is the only option for you to change the fixed variable with respect to time. So if you are working in controls area, this is something which we routinely do, right? You basically saying after this time do this, or if you are doing a batch processing, you say after 5 minutes open the valve, increase the flow rate to this value. So this is what is the task that it does. The task can be time based or condition based. So you can say that these tasks will run based on whatever value it is. Like for example, you say when the temperature is greater than 50 degrees, then run this task. So that you can do here, but those are known as event driven task. This is exactly that was exposed under the cycle organizer. So under cycle organizer, you saw the time driven, that is this guy. When it says event driven, this is event driven. So that is what the cycle organizer does. It is only just for an user perspective. It is done it that way, but you can write everything here, exactly what is happening at the cycle organizer as part of this task, okay? Every time you write it, you must compile it and activate the task. So task, if you double click the task, it will activate. It will be showing like a lightning type of an arrow. When it shows as like a lightning type of an arrow, that means that task is activated, otherwise it is not activated, right? So if you look into here, and we already looked into some of these tasks, so you see that lightning type of thing does not appear here, right? So if I take here and I double click, you will see that there is a lightning type of thing actually shows up here. Sorry, if I take that, okay, they did not let it activate over here. You have to actually put it as part of the overall system. But when you have these as part of this, you just actually can double click on these and it will actually activate that particular task. Okay, it is just simply opening it. Or so that's how you activate activate the task. And then we already talked about this. Okay. One thing, couple of things as you do your parameter estimation and other stuff that you really need to be very careful about is avoiding the potential singularities that you have. Like for example, if I write A is equal to C over B is undefined as we understand if B equal to 0, but if B is equal to 0, it really does not matter as long as we do not have like C equal to 0, non-zero actually. So this assignment, it will be able to solve, it may not converge, but this becomes undefined. So be careful if you are using a division, this should not ensure it does not go to 0. Log x, you have to be careful about the argument of log x, that it should not be a negative value or a 0 value. And then when you have a non-integer n value, you need to ensure that this x should not be negative value. Zero flow often cause problems, so those are always problematic. That is why that Aspentex, that adsorption-desorption simulation is set up like that. It actually does some interesting things in terms of deactivating certain things and reactivating certain things to avoid this failure with respect to 0. So that is an interesting problem, but if you are doing it yourself, never have a very 0 flow anywhere. You just put a very small value and it will still be okay. There are degeneracies that I would like to quickly show here is that think about a degenerate equation. If I am writing an equation, write that, and if I say that f in minus f out is equal to 0, and if I say f in times x GIAN and f out times j x out is equal to j equal to 0, this balance becomes actually degenerate. The issue is that this itself must be. So these are some of the messages that we wanted to be. Equation scaling basically means is, can this residual be between 0 to 1? The other one is the variable scaling. Again, it can be 0 to 1. So for example, if I'm considering temperature and if you're considering in say Kelvin, this could be 300 Kelvin. If I'm considering a mole fraction, this may be 0.001 and say this is 300 Kelvin. Right? I already have a very ill-posed problem with this respect to these. So for this, I can use a scaling. You say T star is equal to T minus, this is the actual T, and then I say T naught over that some T scaling value. So I can shift it and I do a scaling variable, and this could be giving me the T star between 0 to 1. The same thing I can do. Why with these? This is already scaled between 0 to 1, so it's not needed. But for T star or the pressure, if you are using Pascal, you must actually scale it. Use natural scaling. I will always say suggest natural scaling if you can. So instead of Pascal, use BARD, for example. So these things are very helpful from that perspective actually. So this is the case when you write your own equations as part of these type of things. So as I said, use variable and equation scaling, both of them are important. Yeah, it do not have to be 0 to 1, but 1 to 10 is actually pretty good. And you sometimes can use the log function, but you need to be ensuring that the argument itself does not go to 0 or a negative value, right? Plots we have already discussed. I think plots we have already discussed. Yeah. I think that's all that I wanted to have here. Professor Sridhar, you want to add anything that we missed, or you need this one? Oh, you have another one. Okay, good.
So if you have any doubts, you can ask him now.
Anybody has any doubts so far what we discussed? So we still have class tomorrow where we'll discuss some additional aspects, but as of now, is there any other questions based on the material we covered today so far? Is everybody confident about Aspen AdSim setting up an adsorption model? How do I get mass transfer parameters? Assume Professor Sridhar doesn't give you a number. Tell me, is there some water here, or it's all finished? Okay, that's all. Anybody tell me how to estimate the mass transfer coefficient parameter? If we do not have that given from anywhere, how will we proceed in Aspen Custom Modeler? These are the questions going to appear tomorrow in the exam. So we're giving you some glimpse of it in advance. Yeah, take a guess. We discussed all of this today. Sorry? From the literature we can get that, but you will be writing a literature, right? You will be writing a paper. So you have to come up with it because it's a novel thing for you. So how will you come up with it? So what type of data do we need? We need the breakthrough data, right? We need the breakthrough data, and then we like to have a breakthrough under different conditions, like different temperature, flow rate, pressure, and all of that. And then we will solve an optimization problem. Like that was the discussion that which I was having in the morning today, that this is how you estimate the mass transfer coefficient parameters using those breakthrough data. Now, once you have that breakthrough data and estimate the mass transfer coefficient, is this the same mass transfer coefficient you would be expecting when you actually scale up? Like this is from a breakthrough maybe getting from a lab scale. But when you go to a commercial scale, will it increase or decrease? Or what is expected to happen? Any idea, any thought? We cannot say that for sure, but let's take a guess. If we go for a real life, I would just scale it up from like 1 inch diameter in the lab scale to a very large diameter, like 5 meters, 6 meters, 7 meters. Will the performance go up or go down, or why? What would be theoretically will expect? You are thinking might go down, and that is because everything else will come together, and probably there will be more non-ideality that which we could do in a lab scale, right? There is no channeling in the lab because of the small scale, and a graduate student is monitoring that all the time, right? Standing there and turning all the knobs and ensuring we get the greatest results, right? But when you are doing it in a pilot plant, these becomes not like a so easy task there. So yes, those are the things. So carry on. You have anything that you wanna?
So I guess you need more practice. The systems are available. Now we'll go for, we'll take a tea break. Okay, then you can come and practice here. The systems will be available. And tomorrow we'll have a lecture at 10 a.m. tomorrow morning. Okay, by Dr. Devanshu.
Yeah.
Actually for 2 hours, that is followed by evaluation. Okay, then in the afternoon, there is a valedictory ceremony at 3 p.m. Okay.
So if you have any questions, do ask actually, because we'll all need to get ready for tomorrow. And it's not only for, to be honest with you, for the exam, because you came here all for learning. So it's you have an interest here. So if you have any other clarification questions, we'll be all around. And if you want to simulate it, I know some of you are trying like 2-bed system, do that. Under the non-isothermal case, the one I did it for the adiabatic case. So adiabatic case basically means is there is no wall losses, right? But if you say now I have a wall and I consider the losses from the wall, how do I actually simulate that one? If you say, well, I would like to have some user-defined heat transfer coefficient parameter, try one of those procedures options and say, can you make it work, or what are the issues that you find out? Also write those flow sheet constraint equation. You say, I'm interested in this performance measure. So, and we can actually help you to say how to write those if you need any help in terms of that. Analysis, additional features, and giving it Aspen AdSim a harder time, and try it out. Maybe even you use a different isotherm model, like you get it from literature and say, I want to see whether I really understood it, the whole thing, and do it myself. Okay? Okay, let's go for the tea then.